Welcome everybody to the public session of the Event Horizon Telescope collaboration meeting, or should I say Event Horizon Telescope collaboration meeting. I'm not quite sure about that. The pandemic has brought, of course, many challenges to doing interactive science. And I expect that with the climate crisis, there will be more challenges for doing things we are used to in the future. But one advantage that we realized in the Event Horizon Telescope collaboration is that we now have the option to split our meetings between public and closed sessions. So today we have a public session where we can discuss results obtained with the EHT before and their interpretation. In fact, the Cen A result is on the brink of becoming public. So I guess we have some specific instructions for that. I hope our communication has been clear. I can also already see in the chat that people are here to expect the Sagittarius A star results. Our communication should have been clear that that is not on the menu for today. We do feel the pressure to publish Sag star results, but today we are dealing with the previous public results. Before I'm heading over to the chair of the session, can I ask everybody that participates to have identifiable names associated with their accounts? And I would also like to point you to the EHT Code of Conduct, which does apply here today. And I expect everybody to be cheerful and responsible today. So I can head over to another person in the Netherlands who is probably not worried that she cannot watch the football tonight. Sara Markov, you take over.
Sure, thank you so much, Hub. And maybe we can put the schedule up so everybody can see it while I go. Hi, everyone, and happy solstice. Welcome to the only public session of the Event Horizon Telescope's Collaboration Spring Meeting. My name is Sara Markov. I'm a professor of astrophysics at the University of Amsterdam. And within the Event Horizon Telescope collaboration, I'm currently serving as the vice chair of the Science Council, and I co-coordinate the multi-wavelength working group. So anyway, I'm really excited to be chairing this session today. And the main focus is going to be a series of short highlight talks by several younger scientists in our collaboration who have played leading roles in the analysis and the interpretation of our results. And just to explain the schedule a little bit, after each talk, there will be time for just maybe one, maybe two short questions. But then there will be a longer 15-minute discussion after all of the short talks. And for those of you on Zoom link, please post your questions to the Q&A. We'll try to get to as many as we can, time allowing, and I'll read the questions out loud to the speakers to avoid some confusion. And then after the discussion, there'll be a 15-minute coffee break, and then we'll end with the longer 45-minute invited talk by the eminent astrophysicist and 2020 Shaw Prize winner, Professor Roger Blandford. And then there'll be 15 minutes for questions more specifically to his talk afterwards. So let's get started. And I think we're already a little bit ahead of schedule, but that's fine. And we have 3 focus talks to start on the enormous supermassive black hole in the center of the M87 galaxy, which was the subject of our first now 8 collaboration papers. And then we have many more official and related papers as well. And our first speaker is soon to be Dr. Sara Issaoun, and she is just finishing up her PhD at Radboud University in Nijmegen, Netherlands, and will be starting as a NASA Hubble Einstein Fellow in the fall at the Smithsonian Astrophysical Observatory Center for Astrophysics. And so she'll be talking about imaging the M87 black hole and all that that entails. Go ahead, Sara.
Thank you very much, Sara. So I'm really thrilled to be talking to you about 3 of the papers of our amazing M87 series, of course, on behalf of our very diverse EHT collaboration. So in order to observe an event horizon, we have 2 black holes big enough on the sky in order to do that. One of them is the M87 black hole at the center of the M87 galaxy. This black hole is 55 million light years away from us. In order to see the black hole, we need to peer through all of the gas and dust between us and the center of that galaxy. And we can only do this with radio waves. Radio waves are not absorbed by the gas and dust and can reach all the way to Earth. Now, from this galaxy, there is a stream of matter, of hot plasma that comes out. And if we can follow this stream of matter with bigger and bigger instruments, higher and higher observing frequency, we can follow it all the way down to its core, where we observed, our famous image of the black hole in M87. Now, of course, in order to get the resolution to do this, we need a telescope the size of the Earth. Unfortunately, for funding purposes, this is not very realistic to build. So we instead basically piece together telescopes on the Earth as little fragments of a mirror that is the size of the Earth. And we synthesize a telescope virtually via a technique called very long baseline interferometry, or VLBI for short. So how do we do this? So M87 is very far away, and because it's very far away, the radio waves that come from it arrive on Earth as plane waves. So if you have telescopes on the Earth that are far apart so that we can get the resolution needed to make an image, the signals that arrive at the telescopes arrive actually at different times at different telescopes. This is because of the curvature of the Earth. So the baseline distance between two telescopes tells us the resolution of the pair of telescopes, and the time difference between the arrival times of the signal is something we need to take into account in order to align the signals and make sure that telescopes are observing the same thing at the exact same time. So how do we take into account this time difference because of the Earth's curvature? We use what we call masers, or atomic clocks. And these clocks are extremely accurate, and we use them to time tag the data as they arrive at each telescope. We time tag them, and then we record this data onto just standard helium-filled hard drives. We essentially freeze the light that arrives at each telescope and then piece it together at a later time once they're all combined. So building the Event Horizon Telescope was about a decade-long effort. We have, in our 2017 campaign, we had 8 telescopes at 6 different locations. One of them, the South Pole Telescope, did not observe M87 because it is in the southern hemisphere, and M87 is a northern hemisphere source. All of these telescopes happen to be at very high and dry sites where we don't have a lot of atmosphere between us and the source. And this atmosphere is very stable and very dry because water vapor and instability actually scrambles and absorbs our signal before it gets to the telescopes. As you'll notice, all of these telescopes look completely different from each other. The reason for that is that we didn't build them. We actually borrowed them because they happen to be at the right positions to piece together our image. Although they look completely different, they do have something in common. They have receivers installed by observatories and EHT members to observe at 230 gigahertz, the frequency at which we observe with the EHT. And they have our recording equipment, which is our EHT backend, you can see on the left here. Our recording equipment looks exactly the same in every station, and it downconverts our data from high to low frequency, digitizes it to 2-bit sampling, and then records onto stacked hard drives. During our 2017 campaign, we used about 736 helium-filled hard drives to record a whopping 3.5 petabytes of data. About 1 petabyte of data is M87, which we'll talk about today. Now, I mentioned the atmosphere is very important because we need it to be really good weather conditions in order to observe. So we keep a very close eye on the current and forecasted weather, over almost half of the globe, and also our telescope operations to decide when to observe. Of our 12-day observing window, we have 5 observing days to trigger. 4 of them had M87. Luckily, in 2017, we had amazing weather we've never seen before or after 2017 with the EHT, and we were able to record really high quality data. These are some pictures from our observations. Of course, this is a big team effort. We have to thank all our operators and engineers and scientific staff that travel to the telescopes and operate them and carry out our observations. Now, we don't observe alone during the EHT campaign. We also have a wide array of multi-wavelength partners that observe across the entire multi-wavelength band in the X-ray, infrared, radio, TV, etc. These observations also give us a multi-wavelength view of the M87 black hole, which you can see in this beautiful picture and most recently published publication. All of these data are also public, so you can go and have a look at them and see M87 in totally different light. Now, once our data are recorded at the telescopes, they are shipped by airplane because that is the fastest bandwidth we have to our correlation facilities. Correlators are essentially supercomputers that take the frozen light that we had at the telescopes and play it back and then realign the signals, taking into account the Earth's curvature and the positions of the telescopes and different instrumentation effects. One thing the correlator does not take into account is the atmospheric effects in the data, because our atmosphere scrambles and attenuates our signal. That is done at the calibration stage, where we can model the atmospheric effects and other effects not corrected at correlation. We remove them so that we can average down our data, and then that data passes on to imaging. The data calibration and processing step is a 1.5-year process. This is where the data spent most of the time between our observation and the publication of our first M87 papers. So from the correlation stage, we take our data once they're combined into this synthesized Earth-sized telescope. We build dedicated pipelines. So we build 3 parallel pipelines to correct these atmospheric errors and other errors. And then these pipeline outputs are validated by a dedicated team and sent back to correlation if needed to refine the correlation step. And we did about 5 loops of these in order to finally have the right data ready for science. So one of the important steps is this phase calibration, where we can actually create stable and stronger detections and build signal to noise. So this is real data from EHT on 3 different baselines or 3 different pairs of telescopes. In blue are amplitudes, in red are phases. This are the complex visibilities that we observe, so amplitude and phase. This is over a period of about 400 seconds. You see that the phases, these red ones, vary very quickly. We don't expect M87 to vary on such a short time scale, so these variations are actually due to the atmosphere at each site. Because of the high signal to noise in our data, especially because of the ALMA telescope, we can actually make these corrections, track the atmospheric effects, remove them, and create nicely smooth phases like this. Because now our phases are nicely smooth, by averaging, we no longer are deconstructing our signal, we're building up signal and increase signal to noise ready for imaging. So this is what our final data look like. This is amplitude versus baseline length. So short baselines see large scale information in the image, long baselines see small scale information. And you can see that our data form this bounce, which you can follow in this uniform ring guide. This tells us that the ring, there might be a ring structure on the sky. And here you can see that there's 2 levels split. This actually already tells us that there is an asymmetry in the north-south of the ring. All our data are publicly available, so I recommend you go check it out and also make your own images. So what is imaging? So once we go to imaging, we use a technique called aperture synthesis. The Earth's rotation helps us fill our virtual coverage or mirror, and we can combine data on multiple temporal and spatial scales by piecing together all the information we have, and we can see our image coming more and more into focus as we build up data. We use 2 different classes of techniques in order to image M87. We started imaging in a blind imaging stage. We split our imaging effort, which was about 40 to 50 people, into 4 independent teams. 2 teams worked on newer techniques based on forward modeling, and 2 teams worked on traditional techniques based on reverse modeling. The goal was to assess human bias and blindly reconstruct images without talking to each other. After a 7-week period, each team submitted an image, and these were the images submitted. As you notice, each team found a ring of the exact same size with a flux depression in the center and an asymmetry in the north-south direction. The next step was then to understand whether the user-based choices made in the blind imaging actually had a part in the structure where we're seeing. So we wanted to test our imaging software packages systematically in order to understand what each of the knobs in each software does to tune the final image. So we use 3 softwares, 1 traditional method, and 2 forward modeling methods developed specifically for EHT data. So we designed a suite of synthetic data sets to optimize our imaging algorithms with an objective performance assessment. So here we know what the truth should be and what the software should give. And we wanted to get a single imaging script per pipeline with optimized parameters able to reconstruct all 4 of these. And these 4 were actually designed such that the data looked very similar to M87, as you can see here, similar to the data I showed you. But the underlying image could be something completely different. So we tested tens of thousands of imaging parameter combinations systematically using synthetic data sets. The best parameters were then chosen from this test, and those were used on M87 to make the final images. So here are the final images for April 11, 2017 observations for the 3 softwares. If we restore them to the same resolution, they show remarkably similar structure, this ring of the same size, flux depression in the center, and asymmetry in the north-south. Complementary to imaging, we also modeled the data using geometric shapes. So here's an example of, you have a disk, you make a hole in the middle, you can shift it around to make different asymmetries. So we use all these different free parameters in order to model directly the data, and we let the software search for the right parameters that best match the data. And through this search, we found a model that fits the data very well. And again, similar to imaging, it is a closed ring with a flux depression in the center and an asymmetry in the north-south. And the size of the ring ended up to be 42 microarc seconds, which matches also the images. Now, the 3 images from the imaging pipelines, the imaging softwares, were averaged together to actually make the first image of the black hole, this image that you've seen everywhere. That is our April 11 observation of M87. But as I mentioned earlier, during our EHT 2017 campaign, we observed M87 for 4 days. So we actually have other images, not just this one. So this is April 11, and here are the other 3 days. So as you can see, for all 4 independent observations of M87 with the EHT, we see a closed ring with a flux depression in the center and a north-south asymmetry. There are no significant changes during our 6-day span of our 2017 campaign, but you can see some slight changes in the brightness distribution along the ring that also matches some signatures in the data that we see. Now I'll pass it on, and you'll hear more about what all this means in the following talks. Thank you very much.
Thank you very much, Sarah. You were well ahead of schedule, so we have plenty of time for questions. And I'm just looking to see at the moment, we don't have any questions in the chat or the Q&A. So let's give it a second and see if anyone wants to ask something. Otherwise, just to warm people up, one of the things that's nice is that at the end, we do have this discussion. So anytime that we gain, we can, you can think of your questions and then bring it to Sarah afterwards. So with that, maybe why don't we just move on and thank Sarah for her wonderful talk. And we're going to move on then to the next speaker. And oops, I know my timer's going off. So we have Dr. Andrew Chael, who is currently a NASA Hubble Einstein postdoctoral fellow at Princeton University. And he's going to be talking a bit more about the theoretical interpretation, especially in the context of our new polarization results for M87, which he's also going to be covering. So Andrew, go ahead.
Okay, I'm having a little bit of trouble going into presenter mode here for some reason. Oh. Sorry, let me try that again. If it would be helpful to move on to the next talk, maybe.
I mean, we have a bit of time, so if you're ready to just try it again.
Is my screen sharing working? Yeah, I'm trying it again. Sorry.
We don't see anything but a black screen right now.
Oh, sorry.
Okay, do you want us to jump ahead to Leah and then come back?
Yeah, I think you should jump ahead. I can upload it to Google Slides. Maybe someone else can share the screen.
Okay, sounds good. So we're going to have a little change of order, and we're going to move ahead to Dr. Leah Medeiros. And Leah is currently a National Science Foundation Astronomy and Astrophysics postdoctoral fellow at the Institute for Advanced Study, the one in Princeton. And she's also co-coordinator of the Gravitational Physics Working Group. And so she's going to be talking about testing the care nature of black holes with EHT. Go ahead. Leah, you have to unmute yourself.
Thank you. Sorry about that. Thank you, Sarah. I'm going to be picking up where the other Sarah left off. And I had assumed that Andrew would get to present before me, so there might be a couple pieces of the puzzle that are missing, but I hope it'll be clear. I'm going to be telling everybody how we can use these first M87 results to test whether M87 is consistent with a Kerr black hole or not. And before I move on from my title slide, I want to explain to everybody what it is that you're all staring at here, this purple swirly. This is the result of a GRMHD plus radiative transfer and ray tracing simulation. This is actually a free color image. Blue corresponds to 1.3 millimeters, green is 0.8 millimeters, and red is 3 millimeters. And the feature I want to highlight here is this thin white ring. Now, the fact that it's white already tells you that it is achromatic, at least in the wavelength that this particular free color image is probing. And you can also tell that it is completely constant while everything else around it varies quite rapidly. And so this is the feature that is going to be relevant for this talk, and that is the boundary of the black hole shadow. And so what actually is the black hole shadow? So in the literature, there are a few different definitions for this. I'm going to be using two definitions that I think are the most intuitive and the most clear. So we're going to start off with an impact parameter definition. And so in this diagram, the event horizon is in green, the dashed circle is the photon orbit, and all of the red and blue lines to your right, these are photons. And we're going to evolve the trajectory of these photons as they move towards the black hole. And in this case, your observer would be off to the right at infinity. And so as these photons move towards the black hole, you'll see that all of the blue photons fall into the black hole, all of the red photons escape to infinity, and it's these blue photons that create this black hole shadow feature. And another way to think about this is that if you follow, for example, the blue photon that's right at the boundary between photons that fall in and photons that escape, you'll see that it's essentially tangent to the photon orbit. And so another way for you to think about this black hole shadow feature is that the boundary of the black hole shadow is coincident with the lensed photon orbit, and mathematically, either definition will give you the same answer. And so the animation that I just showed you was for a Schwarzschild black hole, but of course we do expect that black holes in space will be spinning. And so the next obvious question is, how does spin affect the size and the shape of the black hole shadow? And so this blue circle here, this is the black hole shadow for a Schwarzschild black hole. But as I play the animation, I'm going to increase the spin. And then once it has a spin, the spin will be pointing up, and you will all be observers at the equator. So as the spin increases, you'll see that the black hole shadow moves over to the right. But at least so far, the size and the shape really hasn't changed that much. And it's only when you get to really high spins that you create this deformation that you see here on the left side of the shadow. And if you calculate what the black hole shadow is for every possible Kerr black hole, you'll find that the radius varies between about 4.8 and 5.2 gm over c squared. That's a range of only about 4%, which is actually quite small compared to the current error bars for the EHT. If you're wondering, for example, why spin doesn't really seem to affect the black hole shadow, what's really happening here is that as you increase spin, you're increasing the quadrupole moment of the metric, and that would tend to make your shadow more oblate. It would be extended horizontally. But as you increase spin, you're also increasing the frame dragging effect, and that would tend to shove part of your shadow over to the right, and so it will shorten it horizontally. And these two effects cancel out almost perfectly due to the symmetries of the Kerr metric. And so now that I've defined what the black hole shadow is in a way that is completely independent of the astrophysics and depends only on the metric and on the inclination angle of the observer, we can then ask ourselves, under what situations or what conditions would this analytically defined feature be either coincident with or close to the observed ring of emission in the images? And so in paper 6 from the first M87 papers, we identified 3 main conditions. And if these conditions are met, then we claim that the ring of emission that we observe is close to the boundary of the black hole shadow. So first, we need to have enough photons so that we illuminate the black hole. Second, we also need the emission to originate close enough to the black hole so that it is gravitationally lensed around it, but primarily outside of the photon orbit. And finally, the surrounding plasma must be sufficiently transparent at the observed wavelength. So in the top right of your screen here, you'll see this kind of orange simulation. That is an animation that's meant to illustrate this third point about picking a wavelength where the plasma is transparent. And so right now, you're looking at what either M87 or Sag A star might look like if you were to observe it at 1 centimeter wavelength. And at 1 centimeter wavelength, you can see this big poofy disk, and you can see these funnel structures as well. Now, it's really important to keep in mind that both Sag A star and M87 are both low luminosity AGN, so we expect them to have these geometrically thick disks as the one that you see here. But at 1 centimeter, they're optically thick. However, if we go to a shorter wavelength, let's say 1.3 millimeters, for example, you'll see that as we go to this shorter wavelength, the disk becomes transparent. We're able to see through the disk all the way down to the black hole shadow. I'm also zooming in here a bit. And again, this kind of thin half circle that you see here that remains constant despite the rest of the variability, that again is the boundary of the black hole shadow. Now, I know it's a little bit hard to see in this color map over here, so I've also included at the bottom here another simulation to try to illustrate the same point. What I've also done is I've taken vertical and horizontal cross sections of the image on the left. And on the cross section plots, I've also included these vertical dashed lines. These are at the locations of the analytically calculated black hole shadow. So as I play this, we'll see again that there is significant variability. There is this peak of emission right at the boundary of the black hole shadow, but it is very, very thin, and the EHT won't be able to observe that precisely. However, if you imagine convolving this emission profile with a Gaussian that has the width of the EHT beam, for example, what you'll find is that it's actually very hard to create a situation where the boundary of the black hole shadow is not contained somewhere within the overall width of this broader peak of emission that you see here. And so this, of course, is the image that Sarah's already talked about, the M87 image. So how do we use these images to test gravity? So we perform feature extraction on these images. And the idea here is that we're using the peak of emission along the ring as a proxy for a measurement of the black hole shadow, but there is, of course, an inherent uncertainty in that. And we also use these feature extraction algorithms to measure the width of the ring as well. In addition to using the image domain, we also perform Fourier domain model fitting, where we fit geometric crescents to the data. And again, we use these results to measure the diameter and the width of the ring as well. And this is just one example of that. And so in this plot from paper 6 of the original M87 papers, we summarize the results of 2 different imaging algorithms and 2 different models that were fit to the data. So the black and green dots here, these are results in the image domain where we use feature extraction. And these blue and red dots here are results from the Fourier domain. Now you will see that all of these results lie along this shaded region that indicates a understood and expected correlation between the fractional width and the mean diameter of these images. And the other thing I want to point out is that there does seem to be a discrepancy in the fractional width between image domain and Fourier domain modeling. And the reason for that is that all of the results in the image domain are convolved with the EHT beam. So it's almost impossible for you to create anything that would be under this dashed line here that's indicating the 10 microarc second beam. Okay, so you cannot use the imaging algorithms to create anything under that line, but the Fourier domain model fitting seems to prefer rings that are below that line, okay? And so we summarize these results in this table here. So the image diameter is 42 plus or minus 3 microarcseconds. This includes only the uncertainty in actually measuring the diameter, not the theoretical uncertainty. The upper bound of the ring width is 20 microarcseconds, but again, keep in mind that if you trust the geometric analytic model fitting, it's actually much, much smaller than that. We use those results to measure the m over d, and then we use that to measure the mass of the black hole as well. So now that we have this mass of the black hole, we can start with our very first test of gravity. And this is really just a null hypothesis test. And the idea here is we want to see whether the size of the ring that we observe is consistent with the prediction for a Kerr black hole. To do that, we need to compare our results with previous mass measurements. Before the EHT, there was one mass measurement that was based on gas dynamics, shown in red, and one based on stellar dynamics, shown in blue. And so if we compare the EHT results with that, the magenta line here is from the crescent models, the blue shaded region is from the image domain feature extraction, and the green shaded region is from comparing GRMHD simulations directly with the data, which I believe Andrew will tell you a bit more about later. And so all three independent analysis methods are all consistent with the results from the stellar dynamics mass measurement. And so the next thing we want to do is go beyond this null hypothesis test and ask ourselves, how constraining is this test? Are we able to rule anything out? And so the idea there is that we want to establish an error bar that includes the uncertainty from actually measuring the ring diameter in the images and the analytic crescent models. It also has to include the uncertainty from the fact that we don't know the spin of the black hole. And so the shaded region on this plot is telling you that uncertainty, that 4% uncertainty. And it also has to include what I call the theoretical uncertainty. And that comes again from the fact that we're using the peak of emission along the ring as a proxy for a measurement of the black hole shadow. And the way that we calibrate that is by using several simulations, and then we create synthetic data from those simulations, and we put that synthetic data through the full pipeline of our EHT data analysis. And then we use that to calibrate and quantify the uncertainty between the peak of emission that we see in the image and the actual analytically defined boundary of the black hole shadow. And so that error bar is 17%. And the way that I usually like to talk about this is that it's essentially the full width of that ring that we see. And so what we're really claiming is not that the boundary of the black hole shadow needs to be right at the peak of the ring, but that it needs to be contained within that full width of the ring that we see in the images. And so 17% is obviously not going to be enough to constrain any part of the Kerr parameter space, as I've already alluded to at the beginning. However, what we can do is we can rule out certain deviations away from Kerr. So the idea here is that you take the Kerr metric and you add different perturbations to it. And you can do this in a parametric way with several free parameters. And here I'm just showing you a couple examples of what that looks like in each of these panels. I'm changing one particular perturbation parameter, and we can see how the size and the shape of the black hole shadow will change as you change that one perturbation parameter. And so we can use these simulations to rule out certain areas of this parameter space. We can place limitations on these perturbation parameters. And so we were able to place order unity constraints on these perturbation parameters. This is what our constraints look like. And here we show the constraints placed on the perturbation parameter that has the largest effect on size for two representative parametrized metrics. And we're showing how those constraints depend on spin on the x-axis here. And the different colors are showing you what happens when you change the secondary most important perturbation parameter at the same time that you change spin and change the primary perturbation parameter. And so you're probably wondering why you should care, right? So we've constrained these perturbation parameters, alpha 1 free, gamma 1 2. You've probably never heard about these parametrized metrics or these particular parameters. So why should you care? What part of the theory are we really testing here? And so we were able to show that the radius of the photon orbit depends only on the GTT component of the metric if you write your metric in aerial coordinates. And we were also able to show that the radius of the black hole shadow also only depends on the GTT component of the metric. And remember that the black hole shadow is really just the lensed photon orbit, which is why we have this relation here. And so the next thing we wanted to do was to compare the results that we get from these parametrized metrics with other metrics and other tests of gravity. And so how can we do this in a coordinate independent way? And what we chose to do was to do what is normally done in testing gravity literature, which is to compare to the post-Newtonian expansion. So here is the GTT component of the metric expanded using the post-Newtonian expansion. And so we are also able to do the same expansion for both of the two parametrized metrics that we are considering in this first paper. And I also want to point out that in the first paper, we set beta and gamma, which are the first post-Newtonian parameters, equal to the values that have been measured in the solar system. In general, the beta and gamma do not need to be the same around a black hole as they are around the sun if you're dealing with a theory of gravity that is not GR. But for this first paper, it was really a proof of concept where we just wanted to show that if we chose to set beta and gamma equal to solar system values, we are sensitive to deviations at the second post-Newtonian order. And so if you do not want to set the first post-Newtonian order equal to the solar system constraints, what you would have instead is a constraint on the linear combination between the first and second post-Newtonian orders, which is shown by this green band here. And in this plot, we're also comparing the constraints from Medeiros, which is the green band, to constraints from two gravitational wave sources as well, which are shown as these two contours. And so we are able to achieve constraints that are similar in precision to gravitational wave constraints. But not only that, the direction of the correlation between the first and second post-Newtonian parameters are almost identical between these two experiments as well. And so we are also, yes?
Leah, you're basically out of time, so can you try to wrap it up?
I have one more slide. And so we're also able to compare to known solutions as well using the 17% error bar. And so instead of using the parametric metrics, we can also use known solutions from specific theories of gravity as well. And that is it. Thank you. Sorry, Sarah, that I went over.
No worries. I just didn't know where you were.
Yeah.
Thank you so much. So thanks, Leah, for a great talk. And now I'm looking to see if we have any questions at the moment specific to this talk. And I'm trying to man both now YouTube, chat, and so on. And I'm also not seeing any open questions. So again, maybe I think we're going to have to defer this to, and then we'll just have time for a longer discussion. And so everybody out there, please think of your questions. And they can also be a bit broader questions if you want to understand more about the general techniques or dig a bit deeper into this. So yeah, I'm still not seeing questions. So let's defer this to discussion. Thanks again. And now, for those of you who tuned in, are just tuning in now, to explain the schedule change, we had some technical difficulties. So I'm going to reintroduce Andrew, Dr. Andrew Chael, who is currently a NASA Hubble Einstein postdoctoral fellow at Princeton. And he's going to be talking a little bit more about theoretical interpretation of our results. Originally, this talk was meant to go after Sara, so it's going to be touching back on how do we interpret these images, and particularly the polarization results that we have just published. So let's go ahead.
Yeah, thank you, Sara, and I'm sorry for the technical issues. Thank you, other Sara, for agreeing to present my slides for me. And thank you to all the organizers for inviting me to give this rapid fire overview of 3 papers, papers 5, 7, and 8 in our series, which are touching on the accretion magnetic fields and jet launching in Medeiros that's illuminated by the EHT. Next slide, please. So the outline for my talk is to first go into what the initial EHT results in total intensity that Sara talked about tell us about the environment around the supermassive black hole. Then I'll move on to how we produced the first polarimetric images of Medeiros, and then I'll talk finally about what we learned about the polarimetric images that we didn't know from the total intensity images. Next slide, please. So first, what did we learn from the initial images that came out 2 years ago? This is EHT paper 5. Next slide. So before the EHT results came out, things we knew about the environment around the black hole in Medeiros, we knew that it was a very massive black hole with a mass of 6 billion solar masses or more. Leah talked in her talk about how we use the EHT results to measure that mass as well. We know that there was synchrotron emission from a very hot plasma with temperatures exceeding 10 to the 10 Kelvin around this black hole, very near its event horizon, and that this black hole launches a powerful relativistic jet to distances outside of the galaxy. Open questions we had at that point, and still have to some degree, are where exactly does the emission come from in this region around the black hole? what is the temperature and the distribution of the emitting electrons? How are they energized and accelerated to these very high temperatures? And then what is the strength and configuration of the magnetic field in this region? And this is something that the polarization results in particular help illuminate a lot. Next slide, please. So when we turn to answering these questions, given the results that we produced from the EHT, we turn to sort of two central theoretical and numerical tools. These are general relativistic magnetohydrodynamic, or GRMHD simulations. These solve the equations of fluid dynamics and magnetic field in the Kerr spacetime. So we get the evolution of the hot plasma and magnetic field as they swirl around the black hole and launch powerful jets. And then we take these simulations and we produce images and movies from them for direct comparison to the EHT data via a technique called general relativistic ray tracing. This tracks the light in the space-time of the black hole as it goes through this plasma and solves for the polarized radiation along those bent light trajectories to produce movies like the one you see on the right here. Next slide, please. As part of the EHT effort, we assembled a large library of these simulations and images, so 43 different simulations with different accretion states, different parameters that determine how the plasma is distributed around the black hole. And from these simulations, we can adjust free parameters that aren't set in the simulations, like the electron to ion temperature ratio. So that gives us even more images out of the simulations, and we produce at the end over 70,000 images that we then compare to data, both in total intensity first and then in polarized light. And this background is just showing you a small selection of some of those images, and you can see how many of the structures are similar. The emission at the photon ring or near the photon ring, but many of the outline structures can be quite different depending on the state of the simulation. Next slide, please. So what did we learn from comparing these simulations to data? I don't have time to get into how we did this comparison, so that's something you can go read the papers about. But what we learned is, for one, the emission is very close to the black hole. So all simulations show the emission region is within a few Schwarzschild radii of the black hole, though it can exist in different parts of this near horizon region. So for example, here are two simulations that could both produce images that look like the EHT, but the one on the left produces its emission in this sort of jet sheath region. You can see the bright spot is where the emission is coming from. You can see that in this case, the emission is coming from along the jet sheath, whereas in the right image, the emission is coming from closer to the equatorial plane, more in the disk. But we know that in all the simulations, the emission is coming from very near the black hole in the region where gravitational lensing is important. Next slide. Another thing we learned from the simulations in paper 5 was that because the emission originates very close to the black hole, it gets dragged around by the angular momentum. The emitting plasma gets dragged around by the angular momentum of the black hole. And so because the orientation of the image is set by the Doppler boosting of the hot plasma, it's the angular momentum of the black hole that determines the image orientation. So we're able to use this fact to determine the direction of the rotation of the black hole on the sky. And we highly favor models where the black hole is rotating clockwise on the sky. And so in other words, the spin of the black hole is pointed away from us. Next slide. So those are two very important things we learned from this initial comparison of data. But then when we try to do more detailed model selection, it turns out that many models with very different physics can be made to fit the EHT observations alone by tweaking the free parameters that we have. That includes adjusting the mass, the position angle in the sky, the total flux density of the source, the distribution of the emitting electrons. All of these things give us substantial freedom to fit many images that come from very different simulations to the EHT image. And here are just 3 images here from paper 5, which all fit the data well, but come from simulations with quite different parameters. So we needed to take the constraints that we have from the EHT image, the constraints about where the emission is coming from and the orientation of the spin, and combine them with external constraints to make more progress. So next slide. And so the big external constraint that we applied was this constraint on the jet power. Sara showed in her talk had this image from the multi-wavelength working group of the EHT showing the jet from the M87 black hole on large scales at many different wavelengths. This jet has been studied over decades now, and we know that it has a lot of power in the jet. So this black hole is launching material with a lot of power out to large distances. the power of the jet is greater than 10 to the 42 Earth per second. And so we insist that our simulations produce a jet of at least this power. Next slide. Once we apply this additional constraint, we reject all spin zero models from the simulation. And we're able to show that once we apply this constraint and we demand that the images from simulations fit both the EHT results very close in and the jet power at larger distances, all in all of these models, the jet is driven by the extraction of energy from the spin of the black hole. So the hot plasma magnetic field is extracting the energy in the black hole's own rotation to drive this large jet. Next slide. That was a result overview of the paper 5 results. Once we had these, we really wanted to know, one of the big open questions was, what is the magnetic field structure around the black hole? And there are two sort of big classes of this field structure in the simulations that we did. Two accretion states that depend on how much flux is accumulated on the horizon. In one state, the magnetic fields are weak and they're turbulent. This is the so-called standard and normal state, so-called normal, I think, because it was researched first. And the other state, the magnetic fields are stronger. They build up coherently on the horizon. You see these long organized field lines instead of these turbulent field lines in the image on the left. This is called the magnetically arrested disk state. And we have simulations of both types in our library, and both can be made to fit the data and the jet power constraint if we adjust the 3 parameters that we have. So our remaining question we have is which of these two states is favored by our data? And just to note here, strong fields in this case means dynamically important ones. It means ones where the field is strong enough to push back against the black hole. For a black hole is push back against the plasma. For a black hole as large as M87, this is relatively weak when you consider other compact objects, so 10 to 50 Gauss, but this is strong in our case. Next slide, please. So to answer this question, the biggest tool that we have is polarization. And this is because polarization in synchrotron emission comes from the fact that as synchrotron radiation is emitted from particles spiraling around magnetic field lines, it's emitted with its polarization direction perpendicular to the field line. So by looking at polarized light, we can learn more about the orientation of magnetic fields in the source. Next slide, please. So we wanted to go from this image on the left, this image on the right. This image on the left is in total intensity, on the right is in polarization, where the ticks on the image show the magnitude and direction of the polarized light that's emitted. Next slide, please. So in this next part of the talk, I'll talk about how we produced and validated the first polarimetric images of M87 in paper 7. Next slide. So this is harder than the initial image reconstruction that Sarah talked about in her talk because we had an additional complicating factor. So Sarah talked about how we have phase offsets from atmospheric turbulence that corrupt our data. We have amplitude gain offsets from telescopes, miscalibration. But now, once we want to image polarization, we also have leakage, which mixes the polarized signals. So we have two channels that we want to image, and leakage mixes these two together. And so we have to overcome these additional factors in addition to the ones that Sarah talked about in her talk for total intensity. Next slide. To do this imaging, we adopted a very similar approach that Sarah talked about for the total intensity image. We used several different types of reconstruction algorithms. We used traditional clean-based reconstruction algorithms. We used these regularized maximum likelihood methods that Sarah talked about. We also, for the first time, used image algorithms that construct full posteriors with MCMC of the individual image pixels. We used all these methods to try to validate each other and get the most confidence in our final result for what the polarized image of M87 looked like. Next slide, please. So we validated these images using a suite of synthetic data tests, as we did in total intensity. The top row here shows all 6 of those synthetic data tests. And the bottom row shows the example reconstructions from 5 different imaging algorithms of the rightmost image in the synthetic data test series. And you can see that all of the different imaging algorithms reconstruct the main features of the polarization in the synthetic data well. Next slide. We also test how well they construct these parameters called D-terms, which determine how much the polarization is sloshing between different channels or leaking from one channel to the other. And I don't have time to get into this comparison in too much detail, but this was the big challenge of the image reconstruction work. And we did a lot of comparisons to show that all of these different image reconstruction methods were performing well and giving similar results on the synthetic data and on the real data for these very important parameters. Next slide, please. At the end of the day, we get results from our 5 different imaging pipelines, 5 very different imaging methods, all produce very consistent results for what polarized emission from M87 looks like. They all show similar polarization structure, with polarization concentrated in the southwest. The polarization angle is predominantly azimuthal, and the overall level of polarization is relatively weak. So the total polarization fraction is only about 15% in the formative part. Next slide, please. And similarly to what Sara showed for total intensity, we produce our final images, which were published a few months ago, by averaging all these different methods together to produce the most conservative results that we can. On the top row shows the image in the style that I've been showing you earlier, where we have different ticks to show the polarization, magnitude, and direction. In the bottom row, you see a different way of visualizing these data, which show the polarization direction as these sort of swirled continuous lines. You can see that the image structure over the 4 days of observation is very consistent, but there are hints of time variability. We can look in detail and see that there is evolution in the structure. We'll need more longer time baselines and more observations in the future to really get a sense of how rapidly and what this variability tells us. Next slide, please. Okay, so in the final part of the talk, I'll talk about what we learned about the magnetic fields from these images that we produced. We went to all this work to produce polarized images. What did we learn from them? And this is EHT paper 8. Next slide. So I told you earlier that synchrotron polarization traces magnetic fields. So you think we might be able to just take the polarization direction we see, rotate by 90 degrees, and get the magnetic field line directions in the emission region. Next slide. It turns out that this is not the case exactly for this particular problem, because relativity and Faraday effects make the situation in M87 much more complicated. Next slide. So very, very briefly, I'll get into both these effects. They're discussed at more length in the paper. Relativity matters because as we trace light back into the space-time of the black hole, the light rays are bending, and that means that the direction in which they encounter the magnetic fields might not be the direction we would naively assume just by tracing them straight back into the space-time. And so these are 3 very idealized examples. This is not what we think is happening necessarily in M87, but this is just 3 different directions of magnetic field and the images we would see from them. On the right, you can see a vertical magnetic field case. We're looking straight down the magnetic field. If there were no relativity and there were no light bending, this vertical case would be completely unpolarized. And in this simple example, with all of the relativistic effects folded in, there is polarization. So that just shows, this isn't exactly what we think is happening, but it just goes to show that relativity and the bending of light in this region is important for producing the polarization that we see. Next slide. Similarly, Faraday rotation matters. So Faraday rotation is occurring on small scales. This is rotating the angle of the polarization that we see. It's happening on very small scales, and so this produces a very scrambled polarization pattern. We look in the simulations. When we blur those simulations out to the low resolution of the EHT, relatively low, we see depolarization, so the sense to blur out the polarization structure and lower the polarization fraction that we see. And it turns out that in our simulations, only this significant Faraday rotation internal that has this blurring effect and lowering effect of the overall polarization pattern can produce the fractional polarization that we observe. So we think that there is significant Faraday rotation that's producing this low polarization fraction. If the Faraday rotation hadn't been important, we would see a much higher polarization fraction in M87. Next slide. Okay, so I will skip over this, but we use many different metrics to compare the simulations, the same simulations we did compared earlier in total intensity to the polarized data. You can see on the right that GRMHD images can produce polarization patterns that look very similar to the images or very different. We use these different metrics, including the polarization fraction and the azimuthal structure to try to constrain which simulations are best fitting the data. Next slide. Once we do
Andrew, you're out of time, so can you tie up?
On my last slide. So once we do this simulation scoring, we take 2 approaches, and both of these approaches, they differ in their details, and so several of the other parameters in the simulation, such as the electron heating, are not well constrained because the different scoring approaches give different answers for them. But both approaches and all the other approaches that we tried strongly favor the magnetically arrested simulations to the simulations where the fields are weak and turbulent. So we took these 2 classes of simulations, both of which could produce images that satisfy the total intensity results, and from the polarization results, we strongly favor these magnetically arrested simulations. And if we There are a few simulations that survive from just the EHT results that in the same case, but if we add the same jet power constraint that we added to the total intensity, that rejects all of those simulations, and we only have MAD simulations. So our polarization results strongly favor this magnetically arrested scenario for M87. Okay, so if you'll skip ahead 2 slides, that's my conclusions. Yeah, so these are my conclusions. We learned a lot about the EHT results from comparing both the total intensity and polarized images. The polarized images in particular tell us that we're really looking at a magnetically arrested disk scenario. And so this is, I think, is a very important case for us to build on with future observations. Thank you.
Thank you very much, Andrew, for excellent talk. And I'm seeing that we don't have any questions yet specifically to yours, but in the meantime, some more questions have been coming in via YouTube and also via the Zoom panel. And so I'm going to start. Oh, actually, sorry, there is really quickly. One just came in for you, Andrew, by Rohit. And he says, sorry if I missed it, but what's the reason for the polarization fraction being low?
Yeah, I'm sorry I had to rush through that relatively quickly. The reason is that this Faraday rotation is rotating the degree of polarization throughout the image, and the amount of rotation is different along different trajectories. So a parcel of plasma right next to a different one will rotate the polarization by different amounts. And once we sort of blur this image to the low resolution that we're seeing it in the EHT, all these different rotation directions cancel out and give us a low polarization fraction. If we had infinite resolution, we would see, we think, very high polarization fractions, but with many different directions. Once we blur it out to our low resolution, we see a smooth pattern, but with low polarization fraction.
Okay, thank you, Andrew. And so now we have a few questions that came in and are sort of, some of them are a bit more general, but I'm going to address them to the speakers in order. So one question came in for Sara from Michael Wondrak, which is, how were the weather conditions this year as compared to 2017? And I suppose we can also talk about the year 2018. Can we expect great new images in the next 1.5 years?
Yeah, that's a great question. Unfortunately, in 2018, we didn't have such a good luck. We actually had pretty awful weather for most of the campaign, except for the first 2 days. But we had the Greenland telescope joining us for the first time, which does make a difference for M87. So already 2018 data have potential to have higher resolution and better coverage for M87 images. Then in our 2021 campaign, we had pretty good weather on our triggered days. And we also had 2 new stations added, the Kidd Peak Telescope and the NOEMA Phased Array. But they also both observe M87, and they add short baseline information. So we can actually hope to see the jet in our EHT images in our 2021 data. So there's pretty exciting stuff coming forward.
Thank you. And we have another question that came in that I think is addressed to Leah. It's from Rema Ahmed. If shorter wavelengths reduce the disks hiding the black hole, why is EHT planning on using higher frequency 345 gigahertz for the next measurements?
Thank you, Sara. Yeah, so the way that you should be thinking about 345 gigahertz is that if you remember that simulation that I was showing you, where we went from 1 centimeter all the way down to 1.3 millimeters, 345 gigahertz is 0.8 millimeters. So we would continue to go in that direction, and you would see even less of the disk, and the bright ring around the black hole shadow would be even more visible. And if you remember, the simulation that I showed on my title slide and my summary slide, the green color in those simulations corresponds to 0.8 millimeters, which is this 345 frequency. And so again, we do expect to see bright emission right at the boundary of the black hole shadow for 0.8 millimeters.
Thank you, Leah. And so I think now we are starting to actually catch up to our schedule. So what I'm going to do, there's a couple more questions, but I'm going to defer them for the discussion after the next 2 talks. And we're going to move on to the next speaker. And these are now a couple talks on 2 additional EHT targets where we can't actually see the image of the black holes themselves, but we can see the inner regions of the spectacular jets that they're launching in much better detail than ever before. And so our first speaker of these two is Dr. Jae-Young Kim, who's a staff scientist at the Korea Astronomy and Space Science Institute and also a guest scientist at the Max Planck Institute for Radio Astronomy in Germany. And he's going to be discussing the results that he led of the paper for the source 3C279.
Thank you, Sarah, for the introduction. Do you see the screen?
Yes, it looks good.
Yeah, okay, thank you. So thank you, I'm Jae-Young Kim, and I'm gonna talk about the EHT observations of another target, 3C279 in 2017. And I want to notice that this work has been also been coordinated by consolidated efforts of many collaboration members. And the result has been published in a paper in ANA last year. So you can refer to that paper for the full details. And we have been talking about M87, and some people are of course getting more curious about Sagittarius A star, but in the context of the astrophysics, I want to emphasize that these are just two sources which are a small fraction of the broad demographics of the whole jetted age, and there are much more questions that we want to answer also at the same time, such as is the jet launching or the accretion physics universal for all the supermassive black holes with jets? Or what's the reason behind the production or the energy dissipation of the gamma ray emitting sources in the high and low power jets? Or what's the origin of the FR1 and 2 dichotomies, which is concerned about the ultimate evolution of the jets? And some new, very new recent discoveries, such as the neutrino detections from a laser. So these are very immediate questions that also can be answered by VLBI, because the VLBI has the, especially at millimeter wavelengths, has the potential to directly image compact the core, the nucleus of the jet-powered sources, and also map the inner jet structure. And by repeated observations, you can also directly monitor the motions in the outflow to determine the kinematics. So that's the unique strength of the VLBI. And of course, the EHT is a very powerful VLBI array. And I want to also briefly introduce to you about the unique source 3C279, which is actually in this field a very old friend with relatively large redshift of about 0.5. So the spatial resolutions that you can get with the EHT beam is actually not as good as those for M87 or Sagittarius A star. So as Sarah mentioned, we cannot image the black hole with this resolution, but you still have a lot of nice and very intriguing features in the sources, such as the very high jet speed and the production and the extreme variability of gamma ray emission in the source. It's really one of the record holders, and the linear polarization in the source is really strong. It's also one of the most strongly and variable polarization source. So that tells that the source has a very highly energetic component, which is also varying and is perhaps highly perhaps with a very coherent magnetic field structure on this compact scale. So the source really, for these reasons, deserves a dedicated millimeter VLBI observation. So that's why the source was actually observed by the EHT in 2017, by the EHT plus ALMA, and in particular in this case, with the addition of a South Pole telescope, because the source declination is lower than M87 and the South Pole can actually see the source. So the source detection is very robust over all the observing days, and you can see in the top panel the images of the source across different observing frequencies. And you can see that in this region, you can see a component which is aligned well with the larger scale jet direction, but at the upstream end of the jet, you see a peculiar, this sub-nuclear structure, which is oriented perpendicular to the larger scale jet, which requires some explanations. So in the collaboration, we also had hot discussions about the interpretation of this image. And one of the best good analogies that we could have made was to look at the space VLBI, the centimeter wavelengths image of 3C84, which is a nearby radio galaxy, which is also very elongated and very compressed, the core shape. And in analogy to this source, and also please see the paper also in detail for the full discussions, but we discussed if this broad nucleus of the 3C279 jet could correspond to also the accretion disk or the base of an edge-brightened jet. So that has some implication for the jet launching in this powerful source. But of course, it's a blazer with a much broader spatial resolution, so we cannot exclude other possibilities such as the oblique shocks, the filaments, or instabilities that are illuminating some parts of the surface of the jet. But although we cannot just simply say pick one of these options as the most promising interpretation, we also found a very significant variability in the data itself. So in the top panel, you see the images across different days. However, the still limited dynamic range of the EHT does not yet allow a very easy identification of the variation of the source in the image plane across days. But in the data, if you look at the closer pace diagram in the bottom left, you will see very clear the day-to-day the variation in the source. And the Gaussian model fitting to the data reveals actually significant motions in day-to-day timescale, about 1 to 2 microarcseconds per day, actually. That corresponds to about 10 to 20, the speed times the speed of light in apparent motion, corresponding to the typical speed that you see in the outer, the jet. And this also signals that the very high sensitivity of the EHT also allows the measurement of motions precisely at the 1 microarcsecond level, besides the imaging resolution. And from the science perspective, this the motion that has been revealed here, this is also very interesting and unique because in the centimeter VLBI observations, you rarely find this. For instance, the centimeter at 15 gigahertz, people found just a few % of the whole monitor jet components showing this behavior. However, these components are usually found in sources whose jets are sharply aligned to the line of sight. So this is often believed to originate from the slight bending of the jet with respect to the line of sight by a few degrees. So that's of course a simple model that we can test with our observables. So that's what we performed in the paper. So in the left panel, what you see basically is to assume a standard from the beginning, the standard jet bulk Lorentz factor. For instance, take gamma equals 20, which is a yellow solid line here. And then you see what if you change the viewing angles of a traveling component through the jet by a few degrees, and see if you can reproduce the observables, such as the apparent speed of the jet or the Doppler factors, to account for the different Doppler boosting that would appear as the different brightness of the components. And we find that actually, for instance, assuming gamma 20s and changing the jet viewing angles from reference about 3 degrees here, just by a few degrees to this red or the gray broken lines, can actually successfully reproduce all the observables, including the bending of the apparent jet position angle. For the details, please check the paper. So this bent jet model is actually surviving very well and is perhaps also more advantageous than other extreme models, which include, for instance, the supermassive binary black holes in the base of the 3C279 jet. And people have done so in order to explain often the bending of the jet on decadal timescale, as you see with the illustration here, one jet going here and the other jet going here. But this kind of this development of the model could be actually, easily biased, because if you do not have the enough angular resolution, for instance, as good as the EHT one, and also with the accurate the kinematic measurement, then you may have difficulty in the accurate modeling of the nuclear region here. So I again refer to the paper for the full discussion to see why we think the bent jet model is at least better than this binary black hole model to explain this observed the phenomenon. And one thing I want to also briefly mention is the very low brightness temperature in the source that we have found in at 230 GHz, because the ground and centimeter VLBI previously have found typically very high brightness temperatures of a hard minimum like 10 to 11 Kelvin. But of course, the sample has some bias, but for 279 specifically, the minimum brightness temperature always was of order of 10 to 12 Kelvin. But what we find at 230 GHz, which is an order of magnitude higher frequency, is at least 1 or 2 orders of magnitude even smaller. So the difference is very significant, and that signals that at millimeter regime, we are really looking at a very different region of this jet, although in image, the alignment between the images look quite coincident. And that also has an implication that at 230 GHz, we are maybe observing finally the fully optically seen the core of this VLBI scale jet. And this generally decreasing trend of the brightness temperature at higher frequencies has been already noted by previous studies. For instance, this one with the references included in the paper also. And although we presented some implications of such a trend, nevertheless, it would be highly valuable to develop more physically motivated models to understand the detailed dynamics of this jet. So one quick summary about what we have learned from this study of 3C279 by the EHT is that this unparalleled resolution and the very high sensitivity provided by the EHT still reveals many new faces of still this very old friend, such as this very peculiar shape of the nucleus and even the day-to-day scale motions that is quite complicated. But this doesn't mean that we are only adding complexity to the source, but we, of course, also can extract much more science, because the first publication was more based on reporting the image and the discoveries. So we hope that with the existing science data, we can already perform the polarimetry of the source at 1 millimeter with 20 microarc second resolution to directly map the magnetic field structure to really see the origin of this high polarization in this source compared to the M87, for instance, which in general has much lower polarization. And finding connection to multi-wavelengths, especially the gamma ray or high energy band light curves, would be fantastic to understand the detailed energy dissipation process in this particular jet at such a high angular resolution. And of course, more sources and longer monitoring would benefit us a lot. But I also want to mention the the future possibly improvement topics. And the one is, of course, to add more stations to the EHT, in particular to find the strong connection and robust connection between the EHT scale and the typical VLBA scaled jet, so that we can really understand how the jet evolves from this compact, ultra compact scale to the milliarc second jet. And of course, as the angular resolution is improving, we are expecting to also find more and more cases like this. What I mean is the inter or perhaps even intraday variable source structure during the course of the observation. So more algorithms to cope with such variability would be highly desirable. And another thing I want to finally add is that the EHT also would greatly benefit by having more functions such as the pace referencing and astrometry, because as you have seen, the kinematics of the source, this well-known source which was considered to be rather boring, already shows a very interesting but also complicated motions. So having an absolute frame, for instance, would greatly help robust analysis of the kinematics to perhaps pin down one of the most promising mechanisms to explain the morphology of the source. I think the time is a bit slightly over, so I will stop here. And thank you.
Thank you very much, Jae-Young, for a great talk and for keeping on time. And at the moment, there are no specific questions. So what I think we'll do is we'll move on then to the last talk of this series, and then we'll have an open discussion. There's a couple questions that are coming in that are more general. Again, like I said, that I'll spread out among the group. So with that, let's move on to the final short talk, which is by Dr. Michael Janssen, who is a postdoctoral researcher at the Max Planck Institute for Radio Astronomy in Germany. And he's led the official paper that is still officially under embargo, coming out in Nature Astronomy about this source Cen A. So you're getting the first exciting preview of these results. And Michael, take the floor.
Yes, thank you. Thank you, Sarah. Very happy to be able to talk about the results of our EHT observation of Centaurus A. Maybe I should, okay, I think now it's better. But our EHT results of Centaurus A. So as you said, the paper is now accepted by Nature Astronomy, and all of these people here listed here, and also the EHT collaboration as a whole, have contributed to make this research happen. As you said, the results are still under embargo, so I'd ask everyone to please not put screenshots of the slides where I show any results. The slide is fine, but for the other slides where I show results, please don't put screenshots of them on Twitter. And to get started, before I will show you actually what we get with the EHT, I want to put Centaurus A a little bit into perspective, so into perspective of what we already know about the source, why it's interesting, and where our new EHT observations actually fit in. So Centaurus A is actually the closest radio galaxy to Earth, and it was among the first discovered extragalactic radio sources in 1950, about 1950. And since then, it has actually been studied across the entire electromagnetic wavelength spectrum by a large variety of instruments probing different scales, different resolutions, and the source at different frequencies. So here in this graphic, for example, the top left, here we see the outer radial lobes of the source. So this is where the jets are terminating and forming these hot bubbles of gas of this galaxy, uncovered by Australian radio telescopes. And here, just for reference, this is how big this source really is on the sky with the moon for scale. And these gigantic radio lobes already are very exciting because they're actually potential sites of where particle acceleration could happen, and where maybe part of the ultra high energy cosmic rays that we measure on Earth might be generated. Then if we zoom in, we see the galaxy on itself. So here we have an image on the scales actually of the galaxy, which here in this color composite image, it has this very famous dust ring in front of it. And for example, here in blue, these are, for example, Chandra observation of the X-ray emission of the jet. So due to the proximity of the source, with many instruments, we can exactly trace what the jet is doing along different scales, and also how star formation is happening, as actually Centaurus A is an active galaxy in star formation. And that makes us actually also a very interesting laboratory for models of AGN feedback. And if we go to the highest resolution images that we have to date of this source, this is what we see. So this is a VLBI image obtained with the 10 Mi array. So here we see this remarkably straight, this remarkably collimated jet on scales of light years. Now, with the EHT, we are actually able to, compared to what we've known previously, so this high resolution image, to get a 16 times better resolution than any observations to date, and have a 10 times an image, also this inner region of this jet where it's being launched at a 10 times higher frequency. So the image I'll show in a moment actually has a resolution of less than a light day. So we're able to probe an extragalactic radio jet on scales of less than a light day. And if you compare that to these gigantic outer radial lobes that have these structures of 100,000s of light years, we are actually uncovering the scales of this jet from where it's launched to find details on light day scales up to this gigantic structure where the jet eventually terminates over 9 orders of magnitude. So we get a very complete picture of this jet across many different scales. And finally, for the EHT, Centaurus A is a very interesting source because in terms of the parameter space of mass and accretion rate, it actually is between our primary targets of that are M87 and Sagittarius A star. And this is the image that we see with the EHT. So this is chromosome-like structure of the inner region of what the jet looks like where it has just been launched. So we have these two brighter arms here, where I think these are this part of the jet. It's moving towards us, so it's Doppler boosted, it's very bright. And we have some emission region on the other side, which we assume is from a fainter counterjet emission that's been deboosted as the jet is actually moving away from us. And the most striking feature here is that in this image reconstruction, we are only reconstructing emission from the jet that is coming from the outer edges. And we seem to have actually no emission whatsoever that seems to be present in the central part of the jet. And we estimate that we have an edge brightening factor here, so the factor by which the edges are brighter than the center, of at least 5. We also assume that these bright regions here, that these are actually the radial cores of the jets where the optical depth becomes unity. Usually these radial cores are unresolved in VLBI images, but here it seems that we're able to actually resolve them. We also see some emission upstream of these radial cores and still not there in the region where the counterjet begins over here. So we assume with this white circle over here that this is the region somewhere where the black hole will be located. I'll talk more about that in a moment. We also fitted the collimation profile of this jet, so essentially how the jet expands as distance towards this assumed apex location of where the black hole is located, and these fits are shown here. So the jet seems to expand with the power law index of about 0.3. So we can compare that to different very similar sources, namely the inner jet of M87, which has a parabolic expansion profile, and 3C84, which has an almost cylindrical inner shape. And for 3C84, one usually assumes that there's a very strong ambient medium present that causes a strong collimation of the jet. So for Centaurus A, we also assume that there is some ambient medium present here surrounding the jet that's causing this overcollimation. And all of these three AGN, they all have in common that they all share a similar edge brightening. So we think, so it seems actually like that this edge brightening seems to be naturally occurring intrinsic and or emerging feature in the jets of low luminosity AGN. But of course, as we are the EHT collaboration, what we really always care about is what would it take to be able to see the black hole shadow of this black hole, so to see the black hole shadow of Centaurus A. And to answer that question, we have to find the frequency where we're actually able to peer down even further towards the jet to a region where we're in an optically thin emission region that is bright. It's also bright enough surrounding the black hole that will allow us to image this region. So because if we go at the too low frequency, we will have this very dominant jet in the way that will be optically thick. And this is actually also what Leah talked about previously in her talk. So to answer that question, we used a standard archetypical jet model in which you have these optically thick surfaces, so the surfaces where the optical depth is unity, that are actually shifting upstream, getting closer and closer towards the black hole with higher frequency. And at the highest frequencies, at some point you will reach really the smallest scale where the jet might be launched, which will be at the ISCO of the black hole. And if we, for example, look at M87, there, based on all their core shift measurements from Hadaidah, for example, it was predicted that in order to reach really the scales of the black hole, you would need millimeter VLBI, which is what we have found verified with the EHT. And if you look at Sagittarius A star, you were actually able to explain the spectrum, so the sub-millimeter bump that we see also with the similar jet model, following similar lines for this source. So if we use this this model, we can just take simply take the core shift that we can compute from our image and simply scale it up to higher and higher frequency until we reach really an emission region that is close at the immediate vicinity of the black hole. And as an order of magnitude estimation for the size of this smallest possible emission region, we've taken the size of the photon ring that surrounds the black hole shadow to try to estimate this frequency where the source is bright and optically thin. Furthermore, we can also look at the fundamental plane relations. So these explain the black hole activity across a wide range of black hole masses based on a simple assumed coupling between the accretion rate from the accretion disk and the power of the jet that's flowing out. So with this fundamental plane, can also compute the same frequency, essentially where the spectrum turns over. And it turns out, so that is proportional to accretion rate to the 2/3, which you can then, again, many simplifying assumptions might relate to the jet power and therefore at the radioluminosity of the jet. So if we take all of these methods into account, we can compute the following numbers for this frequency. So the first is we take the core shift that we have, use our equation, using our equation from before, and then we get a frequency that is somewhere in the terahertz regime. It's relatively uncertain because the inclination of the angle of the source is not well constrained. Then we can use the fundamental plane relations to scale essentially the Centaurus A jet image to the M87 jet image at centimeter wavelength. And from that, we can also compute this frequency, and we see that we get a consistent number that's still in the terahertz regime. With this method also, this would mean that the accretion rate of Centaurus A is about 10% of that of M87. Finally, we can also just look at the core, the spectral energy distribution of the core of the galaxy, and we see that here the spectrum turns over at about 10 terahertz. So we have these three different methods where really the first two are only accurate due to an order of magnitude, due to many simplifying assumptions, but we do get a consistent picture for this frequency for all these three methods. So that gives us some confidence that really, to be able to see the black hole shadow in this source, you would really need to go to higher terahertz frequency VLBI. So to summarize, what we have with the EHT observations of the Centaurus A is that we're able to see the details of an extragalactic radio jet on linear scales that are smaller than a single light day. Combined with all the multi-wavelength information that we have of this source, we're actually able to probe this jet over 9 orders of magnitude in size. Also using this image, we've located the black hole at the jet apex location somewhere, assumed to be somewhere in the circle. And based on that, we predict that in order, if you want to see this region and zoom into this region, you would need to go to higher terahertz frequencies. It's also shown that this estimation, this prediction is actually in agreement with fundamental plane relations. And I should note that usually the fundamental plane is used or is fitted to, on the one hand, stellar mass black holes, and on the other hand, supermassive black holes with masses of 10 to the 8 or more solar masses. So it's interesting to see that this relation still holds in a little bit somewhat intermediate regime of the black hole of Centaurus A, which has a mass of only 10 to the 7 solar masses. Then if you were able to actually do this technological challenge, we're not able to do this yet. If you're able to do really VLBI terahertz frequencies, you would actually be able to resolve the source. You would need a resolution of about 1 microarc-second, already with a baseline of 8,000 kilometers. And as it's terahertz VLBI is very hard and is really impossible to do it from the ground. So this resolution would easily be reached with space VLBI, or maybe even, if possible, with an aircraft like Sophia that is observing at these frequencies. Then for the interpretation of the image, right, the most striking feature is this edge brightening ratio that we're still trying to model and to understand. So there are multiple effects that could cause this. One is that you could have a very thin sheath where all the emission is coming from, or the jet could be strongly rotating, has a strong intrinsic rotation, or there could be, actually, I think the most likely explanation, the presence of very strong helical magnetic field. And we're trying to tackle these questions with our jet simulations, where we try to reproduce this strong edge brightening. And here I show two examples. On the left side, this is an image, special relativity MHD simulation done by Christian Fromm. And on the right-hand side, this is now the full-fledged, large-scale GIMHD simulation that has been done by Kaushik Chatterjee. So we're still working on these simulations and trying to reproduce and better interpret really what we're seeing in this image. And that's all I had. Thank you.
Thank you very much, Michelle. Great talk. And now we have a question that came in actually over YouTube that I think touches on this points that you have on the slide. So I want to pass it on from Johnny, whose last name is almost certainly not real. Can we design a space mission similar to LISA, also in a Lagrange point, but consisting of aligned space radio antennas instead of gravitational wave detectors, and in this way have a larger baseline than Earth? So can you maybe elaborate a little bit more on the idea of space VLBI?
Yeah, I think that really is the dream of many EHT members, because with the current ground station that we have with the EHT, our resolution is limited by the size of the Earth and also the highest frequency at which we can observe at the source before the atmosphere effects of the atmosphere become too extreme. So the natural next step will be space VLBI, and then you, on the one hand side, you could try to do higher frequency. But even if you use the same frequency that we observe with the EHT, you open up many, actually much larger baselines. So you have a much larger separation between your telescopes, which means that you have a high resolution. And probably the next step, there are a few concepts. One is, for example, you could do space VLBI, so you could have multiple spacecrafts on orbits around the Earth that are on slightly different orbits. So they are first close to each other, then they drift out further apart, and thereby really over time you cover, you first start with short baselines, then you go to longer and longer baselines. So you really get a very, what we call a full UV coverage, where you are then able to image a source, both the large scale and the small scale structures. Or we could have space ground VLBI. That's another interesting possibility, where you have spacecraft that observes together with the current ground station that we have in the EHT.
And maybe just a quick follow-up question before we move on to other questions, because it just came in and it's on a related topic from Andrew Chen, which is, would the Russian Radio Astron mission be able to reach the necessary baselines?
I think Radio Astron, correct me if I'm wrong, I think they go out to 10 times, maybe 20 times the Earth diameter. So they have very long baselines, but they don't go that high in frequency. They only observe maybe up to 22 gigahertz, roughly in that order of magnitude, so centimeter VLBI. So that mission delivers very high resolution images of jets, but you see the jets further out, right? You see the jets where they are bright in centimeter regime and not really at the region very close to the black hole, where, as I've shown in my talk, you would need really need higher frequencies. I think the next mission there is also coming, that's millimetron, and maybe with that antenna we can do more at higher frequencies.
Yeah, and we should also point out that Radio Astron was actually used for one of our other targets, OJ287, which wasn't covered today. So it's been a very valuable instrument. And Space VLBI has been selected by ESA as a next technology to explore. So this is good times for that. So now, while you think of more questions out there that are going to be coming in, I have some questions that have already been keeping track of before, and I want to go back to a question that was directed to Jae-Young by David Paneka, which is, you found variability in the EHT image taken over 4 consecutive days. This is about 3C279. Did you see any variability in the optical, X-ray, or gamma ray energies during these 4 days?
Yes, I think I already replied in the chat, but yes, the source shows a very prominent variation, at least in gamma ray. And you can, if you go to the Fermi-related webpage and see the data, you will clearly see that the source has really been varying a lot. And we are actually still analyzing the whole multi-wavelength light curve from radio to gamma ray. So I hope we can really present the consolidated results at some point.
Okay, thanks. And so I had a couple other questions that are a little bit more general, and I'm going to bring them back to the speakers sort of in order. And one also came in from Johnny, and I'm going to direct this to Sara. Are there any new radio telescopes that will join the EHT collaboration in order to increase the resolution?
Yeah, so resolution, not really, because we've kind of ran out of room on the Earth to make, we can't really go wider than the Earth's diameter. But as I mentioned, in 2018, we had the Greenland telescope added to the array. And in 2021, we had the Kitt Peak telescope in Arizona and the NOEMA phased array in France. NOEMA in particular has an amazing sensitivity and will be a great addition to the array. In the near future, there are also plans to add a dish in Africa called the Africa Millimeter Telescope that will also add long baselines to ALMA. They'll be around the same latitude, hopefully in Namibia, and also will be a great opportunity to collaborate more with African scientists. And in the far future, there's a project called the Next Generation EHT, which tries to add also small dishes at lots of different places, because now we have our really sensitive, core elements of the array that are big dishes. So we can add, small dishes at different parts to fill our virtual mirror and make sharper images and images that show, more emission, such as our M87 jet and more emission in Sagittarius star and other also jet sources. So lots of advancement coming up in the future.
Thanks a lot for that answer, Sarah. And there's another more general question that came in from Sai Sidu, which I'm going to direct to Leah, which is the ALMA Observatory sharing data with the Event Horizon Telescope?
Yeah, that's a good question. So the way that things work with ALMA is that the EHT has to propose, just like everybody else, to observe with ALMA. And then for 2017, for example, we were successful in that proposal, and ALMA was a significant component of that array that we observed with, and it gives us increased sensitivity, and it is a very important component of the array. But yeah, I do want to emphasize that we're in a situation similar to the rest of the astronomical community, and we do continue to propose for ALMA time each year.
Okay, thank you. And another question for Michael about Cen A from David Paneka is the jet image of Cen A with EHT with the clear limb brightening seems to have a change in direction by a few degrees of the jet at around 100 microarcseconds. Is this a real feature?
Yeah, that's a good question. Unfortunately, I think the answer is probably not. We ran some synthetic data tests. So what we there essentially do is that we take a known jet image, we pass it through synthetic data generation to generate data that looks as closely as our real data, and then we image that data and see what we get. So we ran some tests with like this bend in there and without the bend, and it seems that sometimes you can get the bend even if it's not present there in reality. So it's really a little bit of a limitation of what we can do with the current EHTs. It was observed 2017, but for these type of fainter features where we're maybe not 100% certain if they're real, future EHT observations, right, when we have more, mentioned before, with more stations, larger bandwidth, only then we will be able to answer this question. I think at the moment, we don't really know if that's real or not.
Okay, so we've kind of run through the main questions that have come. There's one more general question that's a bit more about I'd say the comparison of technologies that was asked, which is, how much more is James Webb Telescope advanced compared to the Event Horizon Telescope, which is kind of a complicated question, right? Because they're very different facilities. Do one of you want to take a crack at answering that? I mean, I think basically, if nobody wants to say, these are very, very different technologies. I mean, in one sense, James Webb is basically just a very large telescope. It's not an interferometric array, and it's also looking in the optical. It has much lower resolution because, when you think about the effective size of the mirror, this is something you have to send up into space, whereas we're using the planet. So it's they're almost like apples and oranges in some sense. But they're also very complementary, right? Because we want to be able to study black holes in many different frequencies and understand their physics in different ways. Now, I'm looking again to see if there's other questions, but I had an idea too, which is we have about a little bit more than maybe about 6 or 7 minutes, and then we're going to have this 15-minute coffee break before we go into Roger Blandford's talk. And so one idea I thought was that quite a few people, both on YouTube, mostly on the YouTube, were asking us, what's the status of Sagittarius A star? Now, obviously, we can't talk about that because we're working on this and it's not out yet. But what we can talk a little bit about is maybe some of the differences between M87 and Sagittarius star that are well known and how this affects some of the analysis that you've heard. So I thought maybe we could go through some of the different speakers, and the different aspects like imaging, polarization, and so on, and jets versus, do we see jets? And maybe each speaker in order can say something a little bit relevant to that. So I guess, Sarah, we could start with you and then move through.
Yeah, so from the data side, so we observed Sagittarius A star during the same campaign in 2017. We observed M87 for 4 of our 5 days. We observed Sagittarius star for all 5. It's kind of our main baby for the EHT, but it is different from M87 because it's a lot less massive, and so because of that, it's very variable. So our data are really variable, and it makes things very difficult, especially to separate what is instrument variation, which we see on very short timescales as well, and what is variation that comes from the source, from Sagittarius star itself. So it's been a challenge to calibrate the data on that sense, and it's also a challenge to image it. So I really like this analogy that imaging M87 is like taking a long exposure portrait of an adult waiting to get their picture taken, and taking a picture of Sagittarius star is like doing a long exposure of a toddler running around a room. And so if you want to do that, you have to investigate how to make variable images, which is movies. And a lot of our time in the imaging is to make sure we understand how these software behave and how they can reconstruct moving structure and how to really understand what we see in Sagittarius star.
Okay, thanks. And so I'm going to direct the same question to Leah, because now you were talking about testing general relativity, and maybe you could say a few words about that. And then there's a question that came in, and I'll bring that up after.
Yeah, so I'm going to build upon what Sara just said and specifically look at how this will affect the tests that I was talking about. And so everything that Sara said about the variability is, of course, a big factor. We also need to account for the fact that we are looking through half of the galaxy when we look at Sagittarius star. So there's also an interstellar scattering screen between us and Sagittarius star. So there are two main factors that make Sagittarius star harder to deal with from a kind of imaging and model fitting perspective. The other thing I want to point out, though, is that Sagittarius star is about 1,000 times smaller than M87, but it's also about 1,000 times closer to us than M87. So as far as resolution, we expect to get very similar overall resolution for Sagittarius star and M87 just based on what the size should be in terms of microarc seconds. Sagittarius star ends up being slightly bigger than M87 based on the distance and the mass of it. So one of the things that is most important to keep in mind for tests of gravity is that part of our uncertainty comes from the previous mass measurements. And so when we're comparing to M87, the previous mass measurements had significant uncertainty in them. However, for Sagittarius star, we have much more precise mass measurements coming from both the UCLA group and the gravity group. And of course, both of those groups just won the Nobel Prize just in 2020. And so because we have such precise mass measurements, it does significantly decrease one of the sources of uncertainty that contributes to the overall uncertainty that is used for tests of gravity. But then, of course, you need to kind of counteract that with the additional difficulty of actually dealing with the data. So it could really go either way. It could be harder or easier. It could be a smaller or larger uncertainty. But regardless, what I always try to point out for tests of gravity is that it's always really important to test gravity in different regions of the parameter space. And because we are looking at black holes that have very different mass, we are testing a different region of parameter space when we test with Sagittarius star versus M87. So even if the error bar for Sagittarius star is much worse than M87, it's still a really worthwhile test to do because you're probing a previously unexplored region of the parameter space.
Great, thanks a lot for that. And now we have a question that was posed originally to Michel about the limb brightening in Cen A from Paul Wilsonak. But I'm going to pass this first to Andrew because he knows quite a bit about modeling magnetic fields, and then maybe Michel can chip in too.
Yeah, so I think it's these limb brightening features we see in the Cen A images are really striking, and moving forward, I think we've done all these comparisons with the EHT. We've developed the whole infrastructure for comparing images of the region right around the black hole to our simulation images. But I think going forward, doing those similar comparisons at these larger distances to jet images to try to understand the origin of these of limb brightening features that we see will become really important. And I think it's actually something that the simulations currently have a hard time producing limb brightening as extreme as we see in Cen A, and even as we see in the longer wavelength images of M87. So whether that's due to plasma effects that we're not including in the modeling, electron acceleration at that sheath region, evacuation of the inner jet that's not included in the simulations. I think we still have a lot of work to do to understand exactly what's causing that very bright limb brightening. And this is something that will be very exciting too. As Sara mentioned, we're going to add telescopes to the array, and so we're hopefully going to be able to see the emergence of the jet in M87 from the supermassive black hole as we go to higher dynamic range. We see lower brightness features by adding more telescopes, even though we don't improve our resolution very much. And so we should be able to see the emergence of the jet in M87, and we can see, is it similarly limb brightened to what we see in Cen A? Is it how is it similar? How is it different? And I think hopefully by holding all these sources together and by taking a look at our simulations and trying to do these comparisons, not just at the very core region, but also along the extended jet, we'll learn a lot about these processes.
Thanks a lot. And Michel, did you have anything else you wanted to add about that?
Yeah, I think just want to add that we are working on it. So we are also trying to image now magnetic fields in Centaurus A, and as we've seen for M87, we know how to do this. So now we have a nice toolkit developed, and now it's like a question of applying this to all the other sources, of course. And what's very exciting for the EHT is the large bandwidth, actually, because the most striking feature to be able to detect if you really have a helical magnetic field is if you study the Faraday rotation of the jet. And if there's a strong helical magnetic field, you would find that it is actually an opposite side on the two edges. And we may be able, with our larger bandwidth in the future, to actually be able to do this within the EHT band, look for Faraday rotation. And with that, we would have really, I think, a smoking gun for the presence of helical magnetic fields.
Okay, thank you so much. So looking at the time, there's about a little bit over 10 minutes before we move on to Rogers, and this is also supposed to be a bit of a coffee break time. So I suggest that we wrap this up. So I'd like to thank all the speakers for the great talks, and thank you all out there for your questions, and keep them coming, because after Rogers' talk, there'll be time for another 15 minutes, although that would be a bit more specific towards his talk. But if, depending on the questions that come in, I'm sure that we can answer them. So anyway, thanks everybody, and let's go to break, and we'll be back at the hour for the start of Rogers' talk.
Is everybody coming back?
I think I see Roger is here. So Roger, are you tuning in? Maybe you can start to test your screen again.
Yeah, I'm. Can you hear me?
Oh, great. Yes, perfect.
Do you want me to share? You want me to share screen, or shall I wait till you say something and then share screen?
Maybe it's better just to share the screen, then we have it all set up when we start.
So.
And then, by the way, Roger, would you like me to give you some kind of 5 or 10 minute warning?
Just in case I get carried away, yes, I think it's prudent to do this, but I will. I am sort of pre-programmed to finish in 45 minutes, I think.
Okay, I'll give you a 5-minute kind of tied up warning if it seems
if
unsure.
it seems like I've got another 3 hours to go. Okay. Thanks. And hi, many old friends on the call, so good to see you.
Yeah.
So I'm going to try and share now, right? Are you seeing that?
Yes,
Yes.
you can see that.
Okay, so I'll now go into presenter view. There we go.
Perfect.
Okay, it looks good. Do you have any movies or anything you want to test quick?
I have one. I guess I must have one movie, and if it doesn't happen, it's not terribly important. So yeah. So let's leave it.
Okay. Let's wait then a couple more minutes, and then when the hour comes, we'll start the introduction. Thanks.
Thank you. Maybe a bit of background noise, for which I apologize. It's somewhat temporary, but there's people working outside.
Okay. Well, it looks like we're on the hour, so probably we should get going just to keep on schedule. So anyway, welcome back everyone from the break. And we're going to have now a 45-minute talk. I'm going to give a quick introduction. And then afterwards, there'll be about 15 minutes for your questions. So anyway, I'm really pleased to be able to introduce to you Professor Roger Blandford. His work has provided the foundation for a lot of the theoretical interpretation that we carry out behind the scenes at the EHT collaboration. And if I read through all of his accolades, we'd never actually get to the talk. So let me just say in brief that after doing his PhD at the University of Cambridge in the UK, Roger moved to the California Institute of Technology, where he was professor for many years before he moved to Stanford University to become the first director of the Kavli Institute for Particle Astrophysics and Cosmology, and also the Luke Blossom Chair in the School of Humanities and Science. And he works on many different aspects of astrophysics, astroparticle physics, cosmology. And to give you some idea of his influence, there are 2 main mechanisms that we consider for how the beautiful jets are launched that you've heard about in some of the last talks, and we name them both after him. So Roger has played a really key role also in determining US national strategy in astronomy by chairing the last big National Academy of Sciences decadal survey about a decade ago, actually the last one. And he's received many awards for his work, and most recently was named winner of the 2020 Shaw Prize in Astrophysics. So we're extremely pleased to have Roger here with us to speak in more depth about black hole accretion and the interpretation of the Event Horizon Telescope results and multi-wavelengths as well. So Roger, you have the floor. Thank you.
Oh, thank you very much indeed, Sarah, for your very kind introduction. I'm going to present perhaps a slightly heterodox or different view of what you might be observing with the Event Horizon Telescope in M87, and I have to say what I'm talking about was more or less my first reaction when I saw your wonderful images. And although the story has moved on a lot since then, and is still moving, as it were. I think there are a lot of ideas out there, and I'm sort of persisting in a stubborn way and looking at things in a slightly different way from the wonderful sort of theoretical interpretations that are in your papers. Because I think there are testable alternatives here, and if that provides some focus for the future observations, which we've heard, the prospects are bright there, then that will be good. So what I'm going to describe is sort of thoughts and ideas that have developed over many years, decades, with many collaborators, and I've only got a small fraction of them here, emphasizing perhaps the most recent ones. And to all of them, I owe a debt, and to none of them should be associated with ideas that they might not approve of. The one person I will call out with is Noemi Globus, who has been helping me, and we've been collaborating on the ideas, and I've not yet really written a proper paper on this stuff. And I apologize for that, but I've been a team of one, but now we're a team of two. And so it's, and I've been a bit slow, so I apologize for that. But as I say, the story has kept on sort of evolving in some ways. So anyway, without further ado, let me just go on to the next slide, the first slide, which is this is redundant because you've just heard an awful lot about these observations in the 5 very nice talks we've just heard, including a couple that had really new things in them, which are exciting. And so I'm not going to talk to the slide because you've seen all of this in one form or another, and you should be familiar with it. No, but if I didn't say it already, EHT truly is a magnificent achievement, both at the scientific and at the popular level. And you shouldn't understate the importance of validating the presence of massive black holes. You didn't see a pentagram there or whatever, has tremendous import, but then all the more detailed things that you can do to follow this up. And I make one other comment. It is a magnificent achievement by the EHT team and an international effort, and all to be applauded, but it also rests on the shoulders of 50 years of extremely hard work developing VLBI from the pioneers in the 1960s through and including, especially, I think, all the unsung heroes in the observatories who made all this work, which was truly astonishing that it was all able to work together in different countries and all the rest of it. Okay, so moving on, jets are tremendous. They're all over the place in totally different environments. Again, I'm not going to speak to this slide. Most of the audience knows about it, but just to drive home the point that you're looking at a mechanism for making jets that is made manifest in very, very different ways. So they're everywhere, essentially. And in this talk, I'm going to mix in a rather confusing and indiscriminate way some sort of theoretical or physical ideas with some observational aspects of the problem, and I'm just going to go backwards and forwards. And I apologize if this is a bit confusing, but I think it's probably the best way to organize it. So let me start out with something, just a very quick summary of classical black holes. As you know, they're observed in the stellar and massive scale, and perhaps in between. They're fully described for the astrophysicist, and we're not talking about the febrile imaginings of theoretical physicists where they're a much richer subject, but just for us humble astrophysicists, they're described by their mass and their spin. They're even more elementary than electrons because they haven't got a charge. And you can measure those mass and spin with a distant spinning planet, for example. And the mass is scale, time, and energy, as you know. The spin is described by a parameter A, that for my purposes will range between -1 and 1, and that's the spin of the black hole. This is the event horizon radius going from m to 2m in gravitational units, and I shall use gravitational units as a unit going forward. So when I say radius is 3, I mean 3 gm over c squared. The angular velocity is proportional to the A for a given event, well, not proportional to the event horizon contains A, but it's determined by A, and the area of the horizon has to increase, as Stephen Hawking showed, and this is an entropy, and on this basis is one of the ways of showing that a black hole contains a rotational energy up to 30% of its rest mass energy, and this is extractable in principle. As is well known, I think everyone here, spinning black holes have an ergosphere within which observers must orbit. And there are, as Roger Penrose first showed, negative energy orbits confined to an ergosphere. And it is possible in principle, as he showed in a thought experiment, to extract energy by arranging a collision or something, or some engineering in the ergosphere, which would put a particle into a negative energy orbit. And is also, I think, now well known, magnetic fields can do the same trick and take that spin energy out. And the contention is that that's what powers the jets. It's common to think about this problem as being both a stage, which is the general relativity. We heard two nice talks that describing how this could be used to test general relativity. These could be used to test general relativity, but I'm going to be much more focused not on the stage, but on the exciting drama that's going on there, and for the purpose of this talk, very much the play's the thing. Okay, so here's a rather facetious acronym to say what I'm talking about here is that basically what you're looking at with EHT and M87 is basically powered by the black hole spin, not by the accretion of gas. And essentially the gas is supplied, it's necessary to confine this magnetic field, but it's driven off by the rotational energy of the black hole, and it's driven off in the disk. And then another key part of this, which will relate to the observations we've just seen discussed, is that the MHD wind collimates the jet. So it's driven off through an MHD wind, and that collimates the jet and starts it radiating through those boundary layers, which have become increasingly prominent. And then just seeing the Cen A images gladden my heart considerably, and I'll come back to that. So there's a bit of a metaphor here in some sense with the sun, which for the 19th century was thought to be powered by gravitational energy. And then it was recognized that this was inadequate. You needed, 100 to 1,000 times more power coming from something at the center. And that, of course, is a nuclear reaction. There are nuclear reactions going on. The same sort of arithmetic is I contend happening here, is that the dominant power comes from the spin of the hole, not from energy released by the accreting gas. So in some sense, there's a sort of structure here, if you like. Then I've just sort of shown this with words here, and you'll see it in pictures. There's a black hole at the center, and it makes a pair of jets. There's a region outside, essentially a sort of clutch, an electromagnetic coupling between the black hole and the infalling gas, which we call the ergomagnetosphere. That the inner part of the gas inflow is through a disk, and it drives two winds, and using another Latin construct, if you like, rather than calling it an accretion disk, we'll call it an ejection disk. And then outside that is an accretion disk, where there's not much mass loss, and so the energy that's released goes off as radiation, and then the whole thing is supplied by gas at somewhere around about the Bondi radius through infalling. So that's the story that I'll be telling. Now, in developing this story, I'm going to make some sort of starting assumptions. I'm going to adopt, I have no reason to doubt the arguments that are given. I'm going to adopt the EHT mass, although, as you'll see, the one that I may need may be slightly different, but it's not going to be very much different. For our present purposes, this is just fine. So adopt the EHT mass. That of course implies that the Eddington limit is enormous, and in its heyday, M87 was probably brighter than Vega is today. That's giga years ago, and so on. It was probably spun up rather quickly. We don't know what its angular velocity is. I'm going to make a pure guess that it's a sort of spinning fairly rapidly, but nowhere near maximally, about a half the maximal value, if you like, A of 0.9 equivalently. That it's still got a rotational energy that's good enough for 1 trillion years at its present rate of jet production, and probably longer. Now, here's something where I am going to take the observations at face value, and I think I'm differing from the philosophy of the EHT models. I'm going to assume that the jets have the sort of the powers that you find in the literature for good reason, that are carried by the jets are about 310 to the 43 ergs per second each. So I'll give them a combined jet power of 610 to the 43 ergs per second. And this is typically larger than is produced in the EHT models. And if it turns out that the powers are 1 or 2 orders of magnitude smaller than this, then the task that we've set ourselves, if you like, becomes easier, but perhaps less necessary. But I'm going to take as a starting assumption that the jet power is essentially what was measured before the EHT images. I'm also going to take, in a similar spirit, that an assumption that the mass supplied at somewhere like the Bondi radius, at 4 arc seconds or thereabouts, is 10 to the 25 grams a second, which is significantly larger than I think is generally presumed in the EHT models. And so again, there are papers which claim that it is significantly less than the Bondi rate if they turn out to be right. And I think we might learn a lot more from Webb on this. If they turn out to be right, then again, the task has become easier and perhaps maybe less important. But this is my sort of starting point. Another important quantity is the inclination of the spin of the black hole and the jets. And I'll follow Craig Walker and his excellent LBI images and assume it's about 163 degrees, again, uncritically, and there's no tilt. Again, all of these things can be changed. Now, on this basis, the ring itself has a power that's much less than the jet power, which was the thing that I've been obsessing about, if you like. Is about 10 to the 41 ergs a second, and in fact, the whole nucleus that might be associated with the disk is probably not much more than 3 times that. We don't know how much more of the power is coming from orbiting gas, but it's probably not much more than 3 times that. So all of these numbers are contestable, but I'm not going to make detailed simulations or models or anything like that. I'm not capable of doing that. But the principles, I'm going to use these to illustrate some principles and see, you can make up your mind whether you think they're important. Now, what sort of stimulated this, and I say most of these arguments are my first reaction, if you like, to seeing the images, was that the jets are very much more powerful than the ring, and so we get these very powerful jets, and yet don't quite understand why M87 is so dim. There's 2 ways of thinking about it. One is you've got an enormously powerful source there, and it ought to be a very, very dissipative structure, having gas orbiting with transonic, transrelativistic, trans-alphanic, and so on. It ought to be very dissipative and ought to be able to accelerate particles like crazy. And then the other thing is the gas that you're supplying. If you trust the Bondi rate, it has a radiative efficiency, if it's conserved, of 10 to the minus 5 c squared. And on average, of course, the Bondi rate is low compared with the average over the lifetime of M87, because it's got to build up its 6 billion solar masses. So now, if the jet is powered by the hole, and this is a little model dependent here, and it's certainly spin dependent, but I'll just take my fiducial numbers, then the magnetic flux in CGS units is 310 to the 33, and that gives you a voltage of about 15 exavolts 300 petamps of current, magnetic fields, which you can measure them two ways. One is a colloidal component of the magnetic field, is about 500 Gauss in unit, where the width of the area of the jet, say, is measured in gravitational radii there. And the toroidal component is about 60, and that, of course, scales inversely, not as the inverse square of the width of the jet in Gauss. And I'll just, for fiducial numbers, I shall take that the magnetic field strength in the vicinity of the ring associated with the jet is about 100 Gauss. Again, this is negotiable a little bit, and there are models that make it less and so on, but this is driven by having a relatively powerful jet compared with some of the models. So on that basis, the cooling time of the electrons emitting at 1.3 millimeters is given by these formula here. The ring, which you essentially measure, if you see it as a ring, then you then deduce immediately that the sort of characteristic beta, and I emphasize here, this is the beta associated with the pressure of the emitting electrons. This is the emitting electrons, not whatever else is there, relative to the magnetic pressure, b squared over 8 pi. That essentially will be B measured in Gauss to the -7/2. So if B is 100, that number is 10 to the -7. And it is this, the actual pressure of what you're looking at is tiny, tiny, tiny compared with a magnetic field that at least is very close by. This was a concern. Okay, now another concern is the jet collimation is physically observed on scales from altitudes of 660 to 10,000, say, and you see the boundary layer, which was just seen gloriously repeated in Cen A, and the magnetic flux, and this requires something to do. This isn't a casual matter. You need a lot of impacting stress to confine that outflow. Remember, these are very powerful jets, so to actually collimate them requires that. Another concern is that the magnetic flux must be tracked, and this requires again sort of 1% or so of a solar mass at least, and probably significantly more. And there are issues of stability in confining the magnetic flux around this. And I'll have a little bit more to say about that. Two other concerns that with the variability. It's there are models which reproduce this, but it's good. And then there's the polarization, which produces naively a poloidal field, and the circular polarization, which ought to be higher perhaps than is reported in the Elmer observation. And I know there are models that can reduce the circular polarization, but on a naive level, I would have expected to see more than you do if you only have electrons doing the synchrotron radiation. So as I say, all of these are addressed in the EHT et al. Models, but at least thinking about it motivated me to think about alternatives. So if you didn't like hemmed in, here's call it a revolutionary hypothesis. And so I'll now come back to the sort of title. And just I want to again go back to some physics. It's probably quite familiar and taught by many of you, but I'm going to take it a stage further if you like. If we look at a traditional accretion disk of the sort that exists only in textbooks, and real ones are much more complicated, I think that we can all agree about, the gas will settle into a thin Keplerian disk at some mass supply radius, which will be the Bondi radius for our purposes. The magnetorotational instability, or its nonlinear development, will cause a friction, and there'll be a general torque, G, acting within the gas. And the traditional disk will have a constant conserved mass inflow, and the energy and the angular momentum and energy have to be conserved. There is no wind. The energy radiated is well known to be 3 times the binding energy released, and the argument in some sense depends on imposing a boundary condition at the innermost stable circular orbit, the ISCO, and where you say there's no torque. That's the way you would do this. And basically what is happening is this excess energy that is radiated at an intermediate radius, this excess energy that is radiated 3 times the binding energy release, there's twice, there's another 2 that's coming up from the torque, that is transported outward from around the ISCO in this case, where there's lots of energy. And so all the energy there's a deficit in release at the ISCO and an excess in over most of the disk. And the key point here is that 2/3 of in the traditional disk, 2/3 of the energy comes from essentially from small radius. And I'm going to write this as two equations here, and basically I'm going to show these again, but let's just explain. Can you see my cursor? Can people see a cursor?
Yeah, we see it, Roger.
Fantastic. Okay, great. So this here is the total flow, excuse me, of angular momentum, and it comprises a torque and then an angular momentum that's convected inwards by the accreting gas. And in this general equation, the essentially logarithmic divergence of this is the angular momentum that's carried off, and it will be carried off through the ejection disk in a wind, shown here, but in the case of a traditional accretion disk, this will be 0. Likewise, the energy comprises the work done by the torque, and then the binding energy, a negative number carried inward, carried by the inflowing gas. But because this is a negative number, you should think about this as an energy that is flowing outwards. And again, its divergence will have two components.
Sorry, I'm having trouble hearing you.
Whoops, sorry. Where are we? This will have two components. One is energy that is carried off by the wind, and the other that is carried off by photons as radiation. Now, if we go to non-traditional accretion disks, as everybody's been seeing in glorious simulations and so on, these are motivated by saying the gas cannot radiate fast enough. It's an old idea going back to the 1970s, Ishimura and others, and they're ion pressure supported. The electrons must be cooler at these mass accretion rates. And there are really sort of two options here. One is the disk remains, the disk heats and thickens, and it's like most of the sort of simulations that have been made, and the mass of energy more or less flows into the black hole. Now the second option is that the disk remains thin, and this is the one that I shall be exploring here. The mass and the angular momentum and energy are carried off in the wind, and there's a gradual transition, if you like, from gas dominance in the outer part of the flow to magnetic dominance close to the black hole. And the winds associated with the ejection disk carry off energy and angular momentum as well as mass. So if we don't look at the nurture, but now look at the nature, then as you've seen, black holes this is old simulation and so on, black holes spin past the jets. Most people seem to be accepting of that, but I would still say that in many of these sources, it is possible observationally that the power can be derived from the disk. So we shouldn't give up thinking about that for sure. So the claim here is the rotational energy powers the EHT ring and drives away the gas. So I'm going to take a sort of, if you excuse the another pun, the holistic approach. And look at these different parts of this big flow from beyond the Bondi radius right down to the horizon, as I say, and I emphasize the principles and the models. So what I'm going to do now is sort of firstly, just as I say, jog backwards and forwards between physics and phenomenology and observation. So I apologize for this, but this is a sort of cartoon that is made on the sort of Bondi scale, and you'll see at the bottom here a radius of 10 to the 6. That means that's about the Bondi radius, 1,000,000 times the radius of the event horizon. So that means not 4 micro-arc seconds, but 4 arc seconds. And what is envisaged, and this is also coincidentally when you deproject, this is about the radius of HST1 if you deproject roughly. And it's where there's clearly going to be a difference in the gravitational potential and probably in the gas properties and the jet properties. And what is envisaged here is that the gas is supplied from high latitude. The inflow is basically quasi-spherical from the cluster, nowadays from the cluster. And so it's a sort of quasi-spherical inflow, and the gas flows in and then settles into a disk somewhere within the Bondi radius, shown schematically here. And the contention is that this outer part of the flow is basically a traditional accretion disk. It's going to radiate modestly, probably in the far infrared mostly, and that's why mid-infrared, I should say, and that's why Webb will be interesting. One of the features, it's not absolutely required, but one of the features of this interpretation of what's going on this larger picture is that the magnetic field has essentially a constant polarity over an accretion time scale at the Bondi radius. So you're looking at essentially a large scale magnetic field that is going to be reflected in the properties of the outflow and the jet, and it doesn't keep on reversing on some dynamo timescale very close to the black hole, to give but one example. And so one of the reasons for saying this is that there's a long-standing puzzle is how come it's elliptical galaxies that are the ones that make the powerful double radio sources. Why not the spiral galaxies? A couple of exceptions, but it's almost always been the case. And a possible explanation for this is that it's this quasi-spherical infall that traps magnetic flux more efficiently than a disk infall in a galaxy like ours, and Sagittarius star for this reason should be rather different, and they will find it easy, the magnetic flux will be able to reconnect and escape much more readily. So the accumulation of magnetic field in this accretion disk going all the way down towards the very center, most of the flux is of course at large radius, but most of the field is at small radius. And typically it's about 10 to the minus 4 Gauss in the outer parts of the accretion disk to about 100 Gauss, as I said, around the black hole, scaling roughly inversely with radius in the very round numbers. So this is a feature of this interpretation, is that the field is let's say unipolar in some sense on this scale and on this time scale, and that is a highly testable proposition, particularly when you think about doing this with the if we now go on to think about what might be going on in this angular momentum, I wrote down and explained these two, the angular momentum and the energy, these two conservation laws, the logarithmic divergence of the angular momentum flux and the energy flux. And I said that in the accretion disk, we'll just say that's zero, fixed by inner boundary conditions. And this is where all the power that is radiated goes. And there's a sort of rearrangement of this. Forget this term for the moment, it'll come up in a moment. Essentially, the power that's radiated is what is inevitably dissipated. This is a very general statement here on the physics. This is inevitably dissipated by, if we've got a torque and a shear flow, there's got to be dissipation. This is the rate of dissipation per unit log radius. And this dissipation is what fuels the radiation that is observed by grateful astronomers. Okay, so let me just break out a little bit from this story and just remind you of some principles of magnetohydrodynamics, which are relevant here. One of the principles, if you think in the language of pop psychology, it's go with the flow. The magnetic field lines move with the gas. And the other, and another precept from pop psychology, is push-pull. And basically that says the Maxwell stress tensor is equal to the pressure, which is isotropic, and the tension along the magnetic field. And the net stress along the magnetic field is equal to minus the energy density, which amateur cosmologists might recognize. I'll say no more about that. It's just a metaphor. But there are, of course, hydromagnetic waves. There are fast alphane and slow waves, and we're interested here just in probably in the fast and the alphane waves that have different kinematics. And I'll come back to this in a moment. But the other important point is that if we have a cold, thin disk, as I'm asserting, then the magnetic field line, as shown over here, that is attached to the disk. If it is inclined formally at an angle more than 30 degrees, but it's a little bit more complicated if you look at real disks, but the principle is still fine. Then a cold lump of gas attached, going with the flow, attached with this field line, will be flung outwards. So these disks can carry away lots and lots of angular momentum by centrifugal outflow going with the disk, and that of course will then, those magnetic field lines will get wrapped around the rotation axis and being pulled inwards by magnetic tension. Ultimately, this must be confined by pressure, but the assertion is that this happens out in this model, this happens at the Bondi radius, and the toroidal field is given by the current I divided by the radius, cylindrical radius R there. So these are sort of principles of, if you like, of MHD. And so this is the thought that the magnetic winds can launch and pinch from the jets. Now going back on a smaller scale on our set of cartoons, looking at what the flow might look like. Here, I'm sorry to Jae-Young Kim, I've distorted his image, his beautiful image, and this is what it would look like from the side, as it were, if Walker was right about the inclination. And this is sort of more, this cartoon is more or less mapped to this, where you start to see the collimation occurring on scales of 500 gravitational radii. And basically what we have, a jet that's coming from the black hole. We have now an ejection disk here, this green part here, which is an ejection disk. And that ejection disk is driving away most of the energy in the angular momentum from the inflow. And that is in an MHD wind, which is interacting strongly with the jet. So it's an MHD wind, which is interacting strongly with the jet, and that interface is the sheath. Sorry. There we go. That interface is the sheath that is observed most recently in the Cen A observations in this picture box. Life of its own, and it will work its way in. The dynamics. Whoops. I'm not touching anything, and it keeps jumping around. The dynamics is controlled by the impact, which is sort of has a ram pressure component of supersonic flow from the disk, but also the pinching effect of the magnetic field confining the jet. And so this will create a boundary layer where fields will be amplified and particles will be accelerated. There's lots of ways in which that can happen. I haven't got time to describe them here, but this is the natural place to get the emission as observed. Going on to a smaller scale now, and I'm going to say a little bit more about the transport in the accretion disk here. Here, the key to this interpretation is understanding what happens to the mass, the angular momentum, and the energy. And let me just amplify a little bit here. Here we've actually got a wind. So the angular momentum that's carried away by the wind at the disk has two components. One is essentially leaves the disk essentially cold, leaves the disk, sorry, with the angular velocity of the disk and no real velocity perpendicular to the disk. So it has just the Keplerian angular velocity, and then in addition, there will be a magnetic angular momentum that is associated with the magnetic stresses that carries away angular momentum too. Likewise, for the energy carried off by the wind, there's the binding energy of the gas, there's the magnetic part, and then there's an enthalpy associated with the heating of the gas, which is, in this case, in the ejection disk, the dissipation, the inevitable dissipation, in this case, goes into just heating the gas and not into radiation by assumption. There will be some radiation, of course, but this is thought to be minor. So it'll go into heating the gas, and it doesn't have to be a very large torque. It doesn't have to heat very much, because all it's got to do is to allow the gas to be elevated to a sufficiently high radius to be able to be flung out centrifugally. That's all that's necessary. And so it doesn't have to be very large. The amount of dissipation that's going on, all the heavy lifting, if you'll excuse the expression, is done by the the gas component to the flow of energy. And if we look out in the wind itself, the specific angular momentum, the specific energy, is shown by these expressions, are given, are conserved along the flow insofar as it's perfect MHD. It won't be, but we know from the solar wind that these ideas are not so irrelevant. And I want to just emphasize one point here, which is replacing the magnetic stress by the global quantities, which are useful for understanding the whole system, which are the current flowing through this large circuit and the magnetic flux phi that's threading this region. So the flux that's interior to some radius or some flux surface is given by phi, and this is a way of expressing the magnetic torque that relates to what's going on in the jet. And the bottom line of all of this is that 10 to the 42 ergs per second, intermediate between the luminosity of the ring and the luminosity of the jets, is sufficient transported outwards to expel all the gas in sort of simple models. Okay, so let's move on. I won't, I just sort of basically said this. This is, I'm clearly not going to have time to make all these points. So these are just sort of simple models that show the mass is being lost, in this case, more or less linearly with radius. In the ejection disk, in the accretion disk, the mass flow is essentially constant. And then at a very small radius, there's essentially no mass. We're just dealing with an electromagnetic region, a magnetosphere, very close to the black hole. So let me say a little bit more about the physics, and I just, again, give the whole talk on this topic, but basically there are three ways that one can think about, usually I think about what's going on close to the black hole. The first is the one that I will advertise and use, which is using force-free electrodynamics in much the same way that Clerk Maxwell did, where he thought about the current as a continuous fluid. The force density vanishes. There's no inertia, no pressure, and this is a perfectly reasonable closed system for describing the electrodynamics. An alternative is, which is most of the simulations have been, has been GRMHD. Here we assume there's a significant fluid stress energy tensor in the velocity, and this is undoubtedly relevant to the disks and so on, the ejection and accretion disks. But it's hard to use for jets, and there are density flaws and so on, and there are real issues that are not tackled by this. And for me, it's better to use force-free electrodynamics for the jets and the regions around them. And then the third approach, which has been pioneered by many people, especially Sasha Filipov and his collaborators, and that is to use GR plasma physics. These use particle and cell codes and try and handle the particle acceleration and radiation. Now, there's a point I'd like to make here, is that if you say what is, under the circumstances in M87, what is the gyro radius in gravitational units? It's about 10 to the minus 12, which is essentially the minimum inertia associated with the charge. So you need tiny amounts of charge to carry the currents. The gyro radii are really small. It's not a, you know, it is a continuum problem, I think. And the other sort of corollary has been a lot of work done on pair production and so on, particularly above the horizon. Plasma is awfully slippery stuff, and just a tiny bit of the gas that you've got around, just getting onto those field lines above the horizon, is more than enough. You don't need pair production. It's not hard to have pair production, but it's not necessary, because you're almost certainly going to have enough interchange of gas that it will provide all the charge density you need. Now, just very quickly make a sort of kinematic point here, that there are two force waves. Under these conditions, there are two waves. There are fast waves, which essentially travel at the speed of light, and there are alpha waves which have phase velocities that are slower. And there are critical surfaces, as there are in any of these flows, where the flow speed is the signal speed. And understanding the causality of these flows, it's crucial to identify where these critical surfaces are. And if you're within the alphane surface, then information can carry freely and the flow can adjust. But if you're upstream from the alphane surface, only that associated with the poloidal current can adjust. And so this is key to understanding what's going on in these systems. So I'm not going to, probably I ought to just say a few words here about this, is if we look at the actual jet production itself, obviously I'm assuming the Kerr metric, there are three frames of reference that are important. One is what I call the Boa-Lindquist frame. This is one where the symmetry and the conservation laws say that the energy flowing along magnetic surfaces and the angular momentum flowing are conserved. Then there's what's called a Zamo frame, which is the sort of frame dagging frame. And an observer within the ergosphere must move with, can't be at rest in the B frame, has to move, and the natural frame to move in is in the Z frame. Then the third frame is the M frame, or the magnetic frame, and this is the one where in one of these force-free solutions the electric field essentially vanishes, and you define, as I think people now are quite familiar, there are equipotential flux surfaces and angular velocity and current and so on are conserved along them, angular momentum and energy are conserved along them, and in the and you see energy going out in the B frame, going in the Z frame, and no energy transport in the M frame. It's all kinematics and it's all consistent with conservation laws. And the dissipation that I've been alarmed at not seeing outside in the ring, is not seeing more dissipation associated with it, is taken care of by these field lines because they go into, because all the dissipation happens quite respectably behind the curtain, behind the event horizon, and also, of course, in the jet. So here's the final of these cartoons. And again, there's a lot more to say about this. There are two, I think, classes of models for this sort of ergomagnetosphere, where which is what we claim is what EHT is actually observing, this highly magnetically dominated region. It's the sort of inner edge of the accretion disk, if you like. So you're seeing this, you're seeing this region here. And either you can have, you've got to have a means of a means of transporting the angular momentum and energy, the angular momentum, you should say, of the event of the black hole, or more specifically this region here between the two surfaces that's in causal contact. This is really what you should think about as being in causal contact, and the event horizon is just where the energy goes. It doesn't really affect upstream. And
Roger, sorry,
yeah.
Can I just break in?
2 minutes.
You're coming up on the end of your time, so just checking in.
2 minutes, yes, I'm almost there, believe it or not. So this is one possibility, and you have a direct magnetic flux connection, and we've explored some of these possibilities, and we've done imaging and so on of these, and I'm not going to have time to get into this in this talk. And then the other possibility is the magnetic field lines, as sketched here, go through the equatorial plane, and there we believe that there are instabilities similar to the MRI instabilities that allow electromagnetic energy and angular momentum to cross the flux surfaces and carry a small fraction of the power that's going up the jet out into the disk. A few percent of that is adequate to expel all the gas in this interpretation. So just to go on, I was going to say something about quasars. I was going to say something about 279 and actually Muscle before, but let me just, if somebody wants to ask about this, I'd be very happy to answer. But let me just summarize by saying that these magnificent EHT observations provide affirmation of the black hole model, and we shouldn't, in our excitement, lose sight of that. It's great. The standard interpretation is that we observe a thick iron pressure supported accretion disk, and I emphasize this could still be right. But the long-standing worries about this, it stimulate looking at an alternative that we're actually you are looking at a magnetosphere around a spinning black hole that eventually expels almost all of the accreting gas in a magnetic wind that is also confining those jets and providing the sheaths and boundary layers. And there's a lot of, I've only sort of touched on this, but there's a lot, I think, of observational implications here. And I think, you know, it's not hard to imagine that distinguishing these interpretations is there. And of course, what I'm saying has implications for other sources, stellar and massive black hole sources, and they're all different. And just like people are all different, And as happens in psychology, nature and nurture are both important in these sources. Thank you very much indeed.
Thank you very much, Roger, for this talk. And I see, please everybody put your questions in the Q&A if you can. I see a couple coming in already. And first one came in was actually from Heino Falca. And I actually kind of shared this question a bit too, which is, trying to understand, although you're saying that this is a different regime than GRMHD, in a lot of ways, what you're saying is kind of what we're reproducing in the simulations. So he was asking, what's really the difference between this picture and the GRMHD models? Is it the boundary condition with higher magnetic field or MDOT or lower density in the jet launching region? Which physics do you think is missing in the GRMHD models that would make them differ from your picture? Or is your picture actually already simulated in our models?
Okay, with 60,000 simulations or images and counting, I can't say that you haven't done this, but my reading, I think we're saying, for better or worse, something different in rather key ways. The first is most of the power for what you are observing is coming from the spin of the black hole. Secondly, the gas densities in the region that you are observing close to the horizon, it obviously looks a bit bigger than this because of the gravitational lensing, the gas densities there are orders and orders of magnitude smaller. You're in a strongly magnetically dominated region where the plasma only has a courtesy invitation just to provide the currents and the charge densities. And I didn't emphasize this, but if you try and make emission models there, you can do almost anything you want, but it's not hard to reproduce. I've done this, it's not hard to reproduce the images after convolution and so on that are observed, something that looks like the images that are observed. Basically, the point is, as long as the sort of particle distribution function is roughly orbiting with the field lines as they are orbiting around the black hole. So the field lines are orbiting around the black hole, just like an accretion disk would, and then if the plasma is attached to that. Now, if you have a model where the plasma is flowing outwards along the jet, and in fact you are looking at the jet itself, then I think it is hard to reproduce the image for all of us, because I think the bright region should be rotated through about 90 degrees. So yes, I think it is really very different. What you are looking at is a strongly magnetically dominated region that is energized by the black hole, and it's not an accretion disk with the release of gravitational energy in that accretion disk. I don't know whether that helps.
Yeah, I will point out that there is quite a few of the simulations where you have magnetically, strong fields that are really dominating the inner region, which are lit up depending on the ways people do the prescription. So that might not be that different, I think, in those cases. But
okay, then I'm glad to hear that. Okay, yeah. Well, obviously, what I should do is maybe I can have a conversation with somebody who can point me to the ones that do this. The ones that I looked at seem to be mostly looking at an ion torus.
Yeah. So anyway, so we can move on from that. And I know, let's see, there's a question from someone Richard Anantua, who's asking you, do you believe the M87 jet limb brightening beyond 100 M requires ionic plasma, or perhaps a pair jet dissipating on a narrow return current?
Sorry, the limb brightening beyond 100 M. Oh, and I think what you're looking at there is, hi Richard. I think we've probably had this conversation many times. I think what you're looking at there is the mass from the wind getting entrained into the jet. And one of the things that M87 may exhibit, and I've never been completely persuaded by this, but we heard the same story in Cen A, is that on these somewhat larger scales, you see evidence for a helical magnetic field. And the reason why I've been skeptical is that a helical magnetic field should only be seen really quite close to the black hole. Because the toroidal component of the magnetic field will go down inversely as the radius of the jet, whereas the parallel component will go down inversely as the square of the radius of the jet. It isn't toroidal for very long. However, and this is, I think, an interesting thought. I did put it on one of the slides, but it's, you know, the Cen A might be a sort of key here. It's quite possible is because in that boundary layer, it is the entrainment of wind into the jet. It's this interface that the toroidal field could actually derive from the wind itself, not from the jet. Then I think it's much more credible that a genuine spiral magnetic field in that boundary layer be a spiral. But I think it makes more sense if it actually comes from the wind, not from the not from the jet itself. I'll just make one other sort of observational point. It's an very old one about this interface, and that is that, of course, it's the famous Fariner-Offen-Reilly 1 and 2 dichotomy, which I was a student at the same time that it came up, and it's a source of wonder and amazement and pleasure to me that what seemed like a rather marginal correlation at the time where there were only a few sources has developed and flowered into such a robust clue about what's going on in the sources, the FR1s and the FR2s. And the old interpretation is that the FR1s are sources where all of the momentum is essentially resides in the wind, and so that decelerates the jet, whereas the FR2s, like Cen A and so on, are ones where the opposite is true and the jet carries the wind along for the ride. And so again, I think we're going to learn a lot more from observations like the lovely ones we saw from Cen A, on Cen A.
Okay, thanks. And linking a bit to that, there's a question from Silke Britson. Does this alternative idea help us to derive information on the spin?
Hi, Silke. Yeah, I'd like to think so. There are two parts. There's many parts of this sort of story that are works in progress, as it were, but one of them is trying to understand what the magnetic geometry is close to the black hole, and in a simple-minded way, sort of inspired by people thinking about pulsars and so on. What you could be looking at are basically sort of current sheets, and the current sheets are rather different in the two possibilities. There are others, but the two main possibilities that we sketched, the current sheets do look a little bit different, and the extent of those current sheets, which you could imagine, the next sort of round with Greenland and so on of observations, actually sort of having the resolution to probe if they are really there, that would be diagnostic, I think, of the amount of spin. But I think it's going to be very hard to distinguish, say, an omega of 0.3 from an omega of 0.4, but it would be not so hard, and particularly if you do the imaging, as was pointed out in the very nice talk this morning, if you do the imaging, if you get omega very close to its maximal value or A very close to 1, then things do fall apart a bit, and correspondingly, if A were very small, then I think you don't just have observational problems, you also have energetic problems. The idea that the spin can power the whole lot is very hard to sustain, I think.
All right, and another question now from Dimitris Psaltis. you were mentioning this thin disk, and he was asking what wavelength it comes out. I think you said that you would predict that would be in the MIR, right? But then the follow-up question would be, is how much power would be coming out at that wavelength, and is it consistent with, for instance, the multi-wavelength campaign that we did, where we do have constraints?
Absolutely. Yeah, I mean, this was sort of almost where I started. I think basically my read, and in fact, there were the old spectrum from Preto et al., but I think the multi-wavelength campaign supersedes that now. And there's not much evidence for power that's much more than 310 to the 41 ergs per second, as far as I can make out. It's maybe my misinterpretation of the observations, but I think there are really these upper limits, and that was for us a very strong constraint, because I do take seriously, maybe it's wrong, that the jet power is, 2 orders of magnitude more than this. And so, yeah, there's typically about 10 to the 42 ergs per second in a sort of simple-minded model, and there's no real basis for this. It's just an existence proof in some sense, just positing a torque and what it will do, without having any sort of microphysical understanding of why it quantitatively is what it is. But you can do it with 10 to the 42 ergs per second flowing out through the disk. And if you think there's an accretion disk at large radius, say beyond 10,000 M or something like that, then that would come out in the mid and far infrared. But there's, as never mind the observations, the sort of models of disks have a lot of interesting things happening on those scales. There are going to be spirals in there. There are going to be maybe even star formation going on, in not perhaps in M87, but in other sources for sure. Tomb ray instabilities and all that sort of thing can be happening. So it could be a much more complicated structure than this sort of simple dinner plate that I sketched here.
Okay.
Yeah, but it was a constraint, and yes, we do try to respect it, and I think Webb will help enormously.
Yeah, I mean, if I look at the numbers, we found, of course, we're not measuring exactly in that waveband, but we do have constraints from Swift and Hubble, and it's in that range already.
Yeah.
So now let's see, moving on. So we have a few minutes left, but I think there's enough questions. We can go a teeny bit over. So now a question coming in from Luciana Rizzola, who says, thanks for the interesting and stimulating presentation. You have proposed 2 different scenarios to describe what's going on near the ergomagnetosphere. Do you think one is naturally preferred? If so, why?
I think Noemi Globus and I have debated this quite a bit without taking sides. I think the arguments in favor of the left-hand side, let's see if I can find the diagram. This one, the left-hand side, the arguments in favor of the left-hand side are there will be these magnetic field lines that will be essentially attached to the inner edge of the ejection disk, this sort of transition, this gradual transition region. And it is natural to expect that some of those will flop onto the event horizon where they won't be very well attached because it's a poor conductor, but they will provide a very strong and natural transport of energy and angular momentum from the black hole to the inner edge of the ejection disk. I think that happens very easily in that version. The problem with it is, and I think this is borne out by some of the simulations, particularly the kinetic simulations, is that current sheet ought to dissipate very quickly. And I'm worried if you can sustain this sort of geometry with that current sheet, with the current sheet there. The alternative on the right-hand side of this diagram has drawn essentially no means of transporting energy and angular momentum from one flux surface to the other. And what one has to invoke is the sort of tangling of the field lines. It's essentially going to be more of a tangling than anything else. In a force-free environment that's going to allow one flux surface to pull on the next flux surface and transport enough of the energy and angular momentum outwards. And your target is quite large. Your target can be as high in the disk as the alphane surface. You can go all the way up to the alphane surface in the disk and still have communication with the gas that's flowing inwards at larger radius. And so but you do need to invoke these instabilities, and we think that we have these instabilities, but we're not sure. We need to work more on this to understand how you have one flux surface talk to the next one. But that's essentially as far as we've got. But we think we can see how they're operating, but we're not sure yet. So that's the debate, if you like.
Okay, and another question we have from Laurent Lenoir is, how do the recent polarization results on M87 fit within this alternate theory?
Okay, very interesting. I shortchanged the polarization. Again, my first reaction when I saw them was good. There's a colloidal field there, and you know, at least the right-hand side of this story produces a colloidal field. But of course, as anybody who's played around with ray tracing in these environments knows, you've got to go beyond the cartoons because the kinematics can be quite complicated. Probably the degree of polarization is lower than the cartoon on the right-hand side would indicate. And that is consistent with there being a mean field and a comparable turbulent field that is associated with the transport of energy and angular momentum radially outwards. So putting a random component naturally is supported there, but with a mean field on top of it. The other polarization part here, and I did say this, but let me repeat it because I think it's important, is the circular polarization. Typically, the degree of circular polarization you get from just electrons, say, is 3/gamma, where gamma is the Lorentz factor of the emitting electron at the wavelength you're observing. And this is, on the face of it, if there were just pure electrons there and a uniform field, you would expect larger circular polarization than ALMA at least has reported. Now, EHT may have a different story about this, I don't know. I'm quite content to wait, but the upper limit reported by ALMA was quite low. If there are electrons and positrons there, then you get no circular polarization. But the more I've thought about this, the more I suspect that needs so little gas to provide the emission and provide the currents and everything, that it's hard to imagine even a highly attenuated mass inflow rate not getting onto those field lines. And so you've got an abundance of charge, and there's no real need to make electrons and positrons there. You can do it, it's very easy. You've got exavolts available and you only need megavolts to make an electron positron pair. But so it's very easy to do it, but it's a question of whether you actually do it. So I'm a bit sort of ambivalent about what you're looking at, whether it's pairs or electrons.
Okay, thank you. And then there's a question, I guess, referring to the slides you skipped from Maciej Vilgus, which is, so what about quasars?
Okay, thank you, my friend. Okay, all right. So quasars, I'm not so crazy as to say that all quasar emission comes from the spin of the central black hole, though I think it's important for the jets and so on, and it does have a role to play there. But here, one of the thoughts is another idea is that and it relates to the VLT gravity image story, which is ongoing. These are spectacular, these are spectacular observations too. We live in lovely times. The idea is that there's a sort of corresponding mass outflow from the disk, and the broad line region really is the gas that's flung out centrifugally from an outer disk, and that's where the gas comes from, and that has very clear kinematic implications for the BLT type images. Point number one. Point number two, and this relates to Jae-Young's lovely presentation on 3C279, but it's much bigger than 279. The problem is, for me, you know, I'm part of Fermi, and this is what greatly surprised me, is you're seeing this gamma ray variability on timescales of 3 minutes in the frame of the source. And yes, you can do all this by relativistic gymnastics, but do I really believe that that emission's coming out from the broadline region, 10 to the light year away from the black hole? If you want to make that emission come from very close to the black hole, then one way to do this is to have an outflow from the inner part of this quasar disk that shields the jet, which you are looking down at these times of rapid variability. You're looking right down it. You shield the jet from the ultraviolet radiation that would otherwise provide enormous pair production opacity. And then there's another very heretical idea here, is that when you look at the famous two-hump spectrum associated with blazars, it is well known and well taught that the left-hand hump is synchrotron and the right-hand hump is Compton. On this viewpoint, it's harder and harder to believe that you're looking at Compton scattering. It's already pretty hard to believe it's Compton scattering, and the claim is that you're really looking at synchrotron emission in the gamma rays all the way up to the highest gamma ray energies. And what is going on there is that there's protons that are accelerated to extra electron volt energies. They create pairs of enormous energy, which do the radiating by the synchrotron process, and the pairs are created by the so-called beta-Heitler process, where a photon comes in and pair produces in the Coulomb field of the proton that's been accelerated to an extra electron volt energy. So that's the story, and this also relates to the idea that neutrinos and ultra-energy cosmic rays have a source in these regions.
Okay, thanks. And I think given the time, we'll do one more. And so this is coming from Michelle Janssen, but I'm also going to add my twist to it, which is, do you think the same model could be applied to Sagittarius star? And I want to kind of add to this and say, you know, you brought up the scenario that, of course, the feeding is quite different and the accretion flow would be quite different, you know, between M87 and Sagittarius star. And so, you know, I would pose this also as a question of, if you were a betting man, would you think that the differences between Sagittarius star and M87 in terms of jet production has more to do with the magnetic field strength or the spin of the black hole?
I'd love to be able to go out on a limb and make some exciting prediction, but not only, I think the difficulties in trying to think about Sagittarius star, we know so much about it, and you know, the recent Nobel Prize is a testament to what spectacular observations there have been, and they're still going on. And you know, when you're ready to produce your paper, that will obviously tell us a lot more too. And it's obviously going to be very hard to do it. But the point I made, firstly, the mass supply rate, it has to be very, very much smaller. Secondly, it comes in presumably mostly equatorial from that molecular torus at 1.7 parsecs. Thirdly, there is, as Russell and Quartiers and others have emphasized, a quite credible source of gas from the hot stars and so on, presumably at high latitude. So maybe, you know, so where does that leave the magnetic field? It does not produce jets, the black hole in air, but it's not got very much power supply. All it produces these rather pathetic Fermi bubbles, which are an exciting discovery, but they're very low luminosity things. So I don't really know what the magnetic field is going to look like. I don't even know what the dominant gas supply like. Is it the stars or is it the molecular torus? Lena Merchikova did some lovely observations which gave us some clues as to what the gas flow in a disk might look like. And I'm just so confused by the observations we have already that I'm not, that I don't feel that I can usefully make any prediction about what you're writing your paper on, except that I will be even more excited and confused by when I see it.
Okay, well, I think that's a great place to end this session. So I'd like to thank Roger again for this talk and for everybody for all their questions and making this a really exciting and interactive talk session. And with that, I think we will close. So thanks everybody, and see the rest of you during the rest of the week at the meeting.
Thanks, Roger.
Well, thank you very much, and nice to see many old friends, and good luck with your meeting.
Thanks very much, Roger.
Yeah, thank you.
Okay, hi, yeah.
Are we still on YouTube or no?